presentation, statistical thermodynamic models for hydrogen diffusion in metals and alloys. The development of metals physics and material science in the coming decades is one of the main driving forces of the new scientific and technological revolution, which will cause significant changes in many sectors of industry and energy, construction and agriculture, military equipment, and everyday life. Diffusion of hydrogen in metals and alloys is very important, as it leads to engineering problems related with manufacturing and use of high-strength steel, reactor materials, alloys for transporting and storage hydrogen, etc. Hydrogen atoms have...
I'm sorry, your presentation is not online. You should check it. Dear colleagues, can you see the presentation of Dr. Babu?
You can see presentation.
Because our colleagues told us that there is no your presentation in online.
Share. Oh, yes. Can you see my presentation? I share with my screen.
Right now we can see.
Yes, we can see.
You can see, okay.
Yes,
okay.
We can see online also.
Okay,
Thank
thank you.
Thank you.
I will continue.
Thank you.
Hydrogen atoms have an extremely high diffusion mobility in solid metals. It is almost the same as in liquids. This high diffusion mobility is thought to be a result of a very low activation energy due to the quantum statistical nature of hydrogen. The purpose of this work is development of the statistical thermodynamic models, hydrogen diffusion in metals, its application for calculations of the diffusion coefficient hydrogen in metals in alloys. This project was founded by the Swedish Foundation for Strategic Research to contract. Okay. The development of material science computational methods in the 21st century is moving from physical, chemical, and phase field methods through various molecular dynamics methods to quantum mechanical methods. There are various diffusion mechanisms, but the two most commonly used are vacancy diffusion, forced diffusion in metals, and interstitial diffusion for impurity atom in metals. We will consider the interstitial diffusion mechanism for hydrogen. Hydrogen can be thought of a statistical gas diffusing through the periodic potential produced by metal atoms. And so this system offers as an excellent implementation of the statistical thermodynamic concept of energy side distribution. The atomic theory of diffusion has an expression from the pre-exponential factor of diffusion that depends from the square of the distance between two atomic positions. Very known equation. The Einstein relation between the mean square displacement and diffusion coefficient is expressed as form equation 2 and have the same relation. However, the main driving force in the theory of diffusion is the gradient of chemical potential of the component of the system. This should be considered when finding equation for the diffusion impurity atom in metals. In statistical thermodynamic equation describing diffusion of hydrogen and carbon in metals have been known. Statistical thermodynamic model of atom diffusion in a crystal lattice of metal was developed in Iron and Steel Institute of National Academy of Science of Ukraine. This is my work 1. The number of diffusive atoms in each state was determined by the Boltzmann distribution. First of all, I obtained the dependence of the diffusion flux.
I'm I'm sorry, I apologize that I interrupt you. Again, your presentation is not changing in online.
Not changing.
We saw the previous, the first one slide we saw previously.
I tried to share and did big. Yeah, I see. I share my screen. Yes, and I.
Right now is okay? Oh, everybody said that right now is okay.
Okay.
See the presentation.
I will continue.
Thank you so
First
much.
of all, I obtained the dependencies of the diffusion flux on the chemical potential gradient, which is the basis of non-equilibrium thermodynamics and phase field modeling. Second, I derived the expression for the pre-exponential factor of the diffusion coefficient from ab initio calculations. The experimental and calculated estimated results I presented in this table. We can see very good agreement between calculated value of hydrogen diffusion coefficient and experimental value. This is part one of my presentation. Statistical thermodynamic model of hydrogen diffusion in metal and alloys, preferably at small concentration of hydrogen. Theoretical method. In the classical limit and using the random walk model of interstitial diffusion in the BCC lattice, the zero diffusion coefficient in the Arrhenius expression for the diffusion parameter can be represented in form 1. Care presented another description of hydrogen diffusion, assumed that the lattice vibration has the same minimum energy saddle point configuration. For BCC metals at room temperature, Care represent this expression or equation 2. What the zero diffusion coefficient depends from temperature. In work 1, it was proposed to use statistical thermodynamic model expression for the pre-exponential coefficient. This approach, based on the first principle of statistical thermodynamics, make it possible to adequately consider the statistical distribution of impurity atom according to their energy. In this case, the diffusion coefficient for impurity atom in metals is determined by equation 3. In the developed statistical calculation model, pre-exponential factor d0 of hydrogen diffusion can be calculated from equation 5. Expression 4 and 5 of the developed statistical model significantly differs from the expression used in simple molecular dynamics. The interpersonal distance d enter this expression to the first degree. But the formula assumed the dependence of d0 on the square of the atomic number of the diffusion element and the square of the temperature. For metals for which the activation energy is still unknown, we use the correlation relationship between the activation energy of hydrogen diffusion and the melting temperature of the eta element T-melt in expression 6, where K is the Boltzmann constant, K0 is the constant coefficient. For the hydrogen diffusion coefficient of alloy, we used the linear mixing formula 7. For practical calculation of hydrogen diffusion in alloys, a software-based statistical calculation model, SCAM, was developed and implemented. It included first principle calculation of diffusion coefficient according to a statistical thermodynamic model, physical-chemical of first principle calculation of activation energy for elements, metals, and silicon, and linear mixing model of of coefficient diffusion in alloys. Basic element for what we consider this is iron and BCC metals. Figure 3 shows two types of the interstitial sites in the PCC lattice, octahedral and tetrahedral. It has been suggested in many works that hydrogen fit better in T sites than in O sites. This simple assumption has been confirmed by DFT calculation. Let's consider the movement of hydrogen atom between tetrahedral sites. The most probable trajectory for the migration of hydrogen atom from one T site into the nearest neighbor T site is via S site, as shown at figure 3. The S site is set like a saddle point along the minimum energy path map, direct hopping of a hydrogen atom between two closing T sites. The length of a single jump of hydrogen atom from one site is a bit more than 1/4 of a lattice parameter. We used this in our calculations. Comparison of experimental SKM calculated data of the value of hydrogen diffusion parameter for metals I presented on figure 1 and 2. The group of metals is highlighted in the figure by a rectangle: beryllium, alpha, iron, zirconium, vanadium, niobium, tantalum, and tungsten have low experimental value of activation energy for hydrogen diffusion. This indicates the possibility of quantum diffusion of hydrogen at low temperature in these metals. For transportation of hydrogen, we have to use the metals with big coefficient of hydrogen of diffusion coefficient and first of big energy activation, as gadolinium, titanium, and aluminum. Calculated value for activation energy per exponential factor and hydrogen diffusivity in alpha iron are present on this slide. It was shown that diffusion of hydrogen in alpha iron deviates from the Arrhenius equation, which is an additional indication of the dependence of diffusion coefficient on temperature. In the centroid path integral molecular dynamic method, were used to change free energy profile for hydrogen migration at various temperatures. According to this data, at temperature below 300 Kelvin, hydrogen diffusion can occur both through S sites and O sites with similar potential barrier value. We use this important theoretical result in the present work. The change in diffusion coefficient of hydrogen in alpha iron in the temperature range, calculated with different model, I presented on figure 4. Diamonds represent the statistical thermodynamic model result with a potential energy barrier equal 0. We can see a good agreement between calculated and experimental value in especially in higher temperature region. Our approach based on first principle of statistical thermodynamics makes it possible to coherently describe the temperature dependence of the diffusion coefficient hydrogen in alpha iron for temperature below 500 Kelvin. However, experimental data on the diffusion of hydrogen in alpha iron at low temperatures near 100 Kelvin are clearly insufficient. Further experimental study of this process followed by a theoretical description, I therefore of higher interest. Value for an activation energy per exponential factor and hydrogen diffusivity in BCC metals what have quantum diffusion and temperature below 500 Kelvin. I represent them in this table. At temperature of 300 Kelvin, average energy of hydrogen atom is very close to the diffusion activation energy in alpha iron and vanadium, what indicate possibility quantum diffusion in these elements, in these metals. As very shown in 4 for the system niobium hydrogen, tantalum hydrogen, the band temperature and the Bayer temperature are very close respectively. In our opinion, temperature close to the Debye temperature for these metals is happening a transition from quantum diffusion of hydrogen equal to nearly to statistical diffusion over the barrier. Calculated value temperature dependence of diffusion coefficient for hydrogen, vanadium, niobium, and tantalum I present on figure 5. The SKM result gives a better description of experimental result of hydrogen diffusion in vanadium, niobium, and tantalum that the Arrhenius equation and temperature above 350 Kelvin in higher temperature region. If we can see what for vanadium, but as statistical thermodynamic results with a potential equal 0 give a most better give a better description of hydrogen diffusion for vanadium. SKM calculated value for activation energy per exponential factor in some important BCC metals I present on this slide. For titanium and chromium, and on the figure 8. For the diffusion of hydrogen in titanium, we obtained very good agreement between the value calculated using the Arrhenius equation and the SKM model over a wide temperature range from 500 to 1500 Kelvin. For the diffusion of hydrogen in chromium, the course of the line calculated using the Arrhenius equation and SKM model does not coincide. However, the difference in diffusion coefficient in the wide temperature range from 1000 to 2000 Kelvin does not exceed 40%, which is a good indicator for the phenomenological equation. For the diffusion of hydrogen in molybdenum and tungsten, we obtained good agreement between the value calculated using the Arrhenius equation and SKM model over a wide temperature range. Diffusion of hydrogen VCC metals the same was calculated with using SKM model. We can see a good agreement between experimental value of hydrogen diffusion in gamma iron and calculated from the SKM model, the red point. And calculated value for other metal I present in this table. For the diffusion of hydrogen in silver, the course of the line calculated using the Arrhenius equation and SKM model does not coincide, presumably due to quantum diffusion of hydrogen in silver. However, the difference in the diffusion coefficient and temperature close to the melting point, more 1000 Kelvin, does not exceed 30%, which indicate the good performance of SKM model. For the diffusion of hydrogen in copper and nickel, we obtained very good agreement between the value calculated using the Arrhenius equation and the SKM model, a wide temperature range. Below we give two examples of using the SKM model to calculate hydrogen diffusion in alloys. First example, this nickel alloys a calculated value together with experimental value. As can see from the result of this table, the SKM model with linear mixing formula gives very good results, both in terms of calculation of diffusion activation energy, we can see very close value, and diffusion coefficient. The SKM model predicts an increase, not a decrease in energy activation by molybdenum. However, even in this case, the difference between the calculated and experimental energy does not exceed 3%. And the value of diffusion coefficient are less than 35%. This one and this one. Second example, the calculation value of a hydrogen parameter in zirconium alloys together with experimental value. The composition of the alloy I presented in this table and calculated value in this table. After laborious DFT calculation for pure zirconium, the value of parameter D0 and energy activation were obtained, which is in good agreement with the parameter of the SKM model. In this case, the diffusion coefficient of hydrogen in zirconium, calculated at 500 Kelvin in SKM model, is closer to experimental value than DFT calculated value. For other alloys, difference in the diffusion coefficient hydrogen at 500 Kelvin do not exceed 30%. Consequently, to estimate the value of the hydrogen diffusion coefficient alloy, SKM model can be used. And conclusion for this part 1. Our approach, based on first principle of statistical thermodynamics, make it possible to coherently describe the temperature dependencies of diffusion coefficient of hydrogen in alpha ferrum and other basic metals. The SKM model with linear mixing formula gives very good results, both in terms of calculation of diffusion activation energy and diffusion coefficient hydrogen in alloys. Further development of this model will occur by taking into account quantum diffusion, tunneling of hydrogen at low temperature by moving from statistical thermodynamic to quantum thermodynamic. This I would like to present to your attention part 2 of what was performed in Uppsala University. Statistical model for calculation of parameter of hydrogen in higher entropy alloys. In the developed statistical calculation model, calculated parameters have been performed with the linear formula 10, where calculated parameter of high entropy alloy, lattice parameter, density of alloy, gravimetric density of hydrogen in alloy, calculated for hydrogen per metal atom equal 1, and volumetric density of hydrogen in alloy. This is additional parameter. In high entropy alloy, the maximum measured storage capacity was 2.5 hydrogen atom per atom metal at 53 bar pressure, which is equivalent to 2.7 weight percent of hydrogen. Alloy with a content of more than 2.5 hydrogen per metal atom have not yet been detected experimentally, which confirms their thermodynamic instability. Such a high concentration of hydrogen will undoubtedly affect its diffusion. We will discuss this question below. Possible position of hydrogen atom is BCC lattice with increasing of ratio hydrogen atom per metal atom. I presented on this slide. We have a description. At the concentration of hydrogen in the BCC alloy is close to the ratio hydrogen atom per metal atom equal 1, it has been experimentally established that hydrogen is located in all sites. This work my collaborator and supervisor, Professor Martin Salberg. The possible symmetrical arrangement of hydrogen along the phase with the minimum total energy in this case is shown in figure 12E. This one. The structure for hydrogen concentration is less than ratio equal 1. I presented in the figure 12. Of course, at small concentration hydrogen places in P sites. But at a big concentration of hydrogen here places and O sites. The lattice in figure 12 with a concentration of hydrogen equal 1 has 4 fill plates and corresponding octahedral spaces between the lattice atoms. Figure 12F shows the structure of symmetric filling of the BCC lattice with 6 hydrogen atoms and all octahedral spaces of the lattice with hydrogen atom per metal atom equal 1.5 with reduced energy. We believe that this is the maximal thermodynamically stable concentration of hydrogen in the BCC lattice. With a subsequent increase in the concentration, the atom of hydrogen should occupy 2 T sites of the same octahedral space between the atoms. This state increases the overall energy of the system and the structure becomes unstable. Therefore, the BCC lattice is translated into a more stable VCC lattice as shown in work 5 for high entropy alloys. Possible position of hydrogen in VCC lattice with increasing of ratio hydrogen atom per metal atom are shown on this slide. A higher local value of entropy in the VCC lattice will occur at hydrogen atom per metal atom equal 2.5 when 50% of all sites are occupied by hydrogen. Finally, the complete filling of the VCC lattice T and O sites with hydrogen determines the structure in figure 30F. It has minimal entropy, low hydrogen diffusion due to lack of free T and O sites. It can be characterized by a compound of the metal hydrogen 3 type, for example, aluminum hydrogen 3. We performed statistical thermodynamic analysis of the embedding solution. let us further consider the thermodynamic property of the abelian solution, considering the interaction of solute atom. In this case, the energy for this solution have describe the equation 10. We begin to calculate the statistical sum of the solution, and then we found the expression for the free energy of the solution takes the form. From this expression, we have the expression for chemical potential of basic element and dissolvent substance, in our case hydrogen. The activity coefficient of the component in this interstitial solution can be determined as follow this expression. We found the total activity of the dissolved component in the solid solution is represented as equation 24 and parametric form. On figure 14, I represented depends the hydrogen activity from the hydrogen concentration in the metals and alloys. For BCC lattice and for FCC lattice. They can found on the way of numerical calculation equation of statistical thermodynamics. These results were obtained for the first time. Let's see to using the SKM model for calculation for calculated value for a density of hydrogen in some high entropy alloys. These high entropy alloys are the composition of the alloys are represented in this table, and calculated value of density, gravimetric density of hydrogen, volumetric density of hydrogen in the alloys. For the perspective composition of high entropy alloys. It has been found that tantal and tungsten to increase the density of alloys and volumetric density of hydrogen in the alloys are the perspective elements of high entropy alloys. The addition of tungsten can increase the volumetric density of hydrogen in the high entropy alloys to a very high value, to a very high value, 121, this parameter, kilogram hydrogen per meter cubic. High entropy tungsten alloy can have the lowest calculated coefficient of hydrogen diffusion, which is necessary for long-term hydrogen storage. This we can see in this table. In this alloys, tuning the interstitial sites available to host hydrogen via the high entropy effect might lead to a higher storage capacity. Experimental value was very close to the calculated value from the SKM model. From the correlation of calculated experimental parameter, the expected value of the lattice parameter of high entropy tungsten alloy was established, this one. Another example of another type of hydrogen, another type of high entropy alloys for hydrogen storage. This with good reversibility and fast kinetic was reported in the C14 Leif's fuzz. As an example, titanium 2, zirconium X, chromium, manganese, iron, nickel, which contain 95 weight% of this phase. Absorbs and dissolves 1.7 weight% of hydrogen at room temperature. Which comparable with other room temperature hydrogen storage material, titanium, this one. We used vanadium instead of zirconium for this high entropy alloys. Vanadium alloys us to obtain the highest hydrogen volumetric density value in the alloy at a content of 3,6 atomic percent in this high entropy alloy. And next example for the hydrogen concentration in metal glass thin films and dependency of diffusion coefficient from this concentration. This experimental differences of the diffusion coefficients of hydrogen at different temperature is this thin films from the work my colleagues Gunnar Palsson. Is this calculated dependency of the diffusion coefficient of hydrogen at different temperature, taking into account the activity of hydrogen from our expression from experimental dependencies of the diffusion coefficient of hydrogen at different temperatures confirm the change in activity with a theoretical model for VCC alloys with K equal 1. In conclusion for this part. For practical calculation parameter of hydrogen in metals and alloys, the statistical thermodynamic models has been developed. The performant statistical thermodynamic analysis made it possible to calculate the activity of hydrogen in various types of alloys and the maximum thermodynamic stable concentration of hydrogen in the alloys. It has been found that tantalum and tungsten to increase the density of alloys and volumetric density of hydrogen in the alloys, and are the perspective elements of high entropy alloys. The addition of tungsten can increase the volumetric density of hydrogen in the high entropy alloys to a very high value. Vanadium alloys us to obtain the highest hydrogen volumetric density values in the alloy at a content of 3,6 atomic percent this element in high entropy alloys. Unfortunately, this linear maximum model does not allow us to take into account all the factors of the mutual influence of element on the parameter of hydrogen in alloys. Further development of this model will allow us to consider influence of this factor of the parameter of hydrogen in high entropy alloys. Thank you, dear colleagues. Thank you for your attention, for your patience.
Thank you very much, Dr. Kabir. Dear colleagues, I would like to open the discussion floor. Please raise your hands. Who would like to answer the question? I'll come in. Okay, I'm coming.
This year's the Nobel Prize in Physics is awarded the scientists for their investigation of tunneling effect. So interesting to ask, what part of diffusion, for your point of view, has ordinary statistical nature or quantum diffusion, or that is
excuse me, sorry, I can't hear you. Its sound is very weak, very weak sound, and with with mixing.
What part in diffusion in your investigation has ordinary statistical origin or quantum origin from quantum tunneling effect? You understand?
No, if maybe I don't understand question at all. But yes, we used a statistical thermodynamic model of hydrogen fusion over the barrier. We can't use the quantum quantum diffusion equal to tunneling through the barrier. We calculated only parameter for hydrogen diffusion over the barrier.
Thank you so much. And who would like to bring next? One more?
So all diffusion is origin quantum tunneling effect. I right under.
I understand. I hear a little, very little. The sound is very weak.
Okay, I see. And maybe one more question. Who would like to ask? Dear colleagues. No, okay, I can see.
For which industries and which products can you develop and then be applied?
Sorry.
About your application, how could you apply your research in the practice?
No, we first of all, high entropy alloys. We can calculate all parameter diffusion for metals and alloys, for all metals and alloys. We have this model, calculation model, what realized in the from the soft, as a soft model. What can allow with allow calculators all parameter diffusion in all metals and alloys, including silicon. At different temperatures. And we can calculate this parameter in high entropy alloy with a big concentration of hydrogen in high entropy alloys. We showed this in our presentation.
Thank you very much. And who can ask more questions? No? Thank you so much, dear Dr. Babir, for the interesting speech. And we are continuing. And the next one is Dr. Turchanin.
Thank you
for thermodynamic study and predicted amortization composition range of the cobalt, nickel, and titanium liquid alloys. Dr. Turchanin, are you here? Can you hear us? Dr. Turchanin. Dr. Turchanin, you were there. Are you here? Please share the screen.
I am sorry. Maybe Professor Turchanin is busy, so I will make instead him our report on this theme. I will start our presentation, if you please.
Okay. And could you introduce yourself? Please introduce yourself. Dear colleague, could you introduce yourself? You're a colleague of Dr. Turchanin, as I understand, yes?
Okay, dear colleagues, with your permission, I will present our report on thermodynamic investigation and prediction of amorphization composition range for the cobalt nickel titanium liquid alloys. The cobalt, nickel, and titanium are the basis for creating technologically important materials for numerous applications, such as superalloys, high entropy alloys, single phase B2 intermetallics, and amorphous alloys. The literature data for the integral enthalpy of mixing for the liquid alloys of binary edging systems are shown here. For the cobalt titanium and nickel titanium systems, the results of investigations indicate significant negative values of the integral enthalpy of mixing. The same case is for activity of components in the liquid alloys of these systems. The thermodynamic properties of liquid cobalt nickel alloys are close in their properties to ideal solutions. The thermodynamic activities of components obey Raoult's law. The research data on ternary system are presented here shortly. The results of investigation devoted to the study of equilibrium phase transformation led to thermodynamic description of this system, but the mixing enthalpy of the liquid alloys was not studied. The great potential of this system is not considered for production amorphous alloys. Although information about the two-component amorphous ribbons, films, and powders is presented. Information on the thermodynamic properties of three-component phases is important for creating thermodynamic database necessary for subsequent development of multi-component materials. The objective is to study the thermodynamic properties of the liquid alloys and to predict the composition regions of amorphization for the melts of the system. Tasks of the work are: first, experimental study of the mixing enthalpy of the liquid alloys; second, modeling the temperature composition depends of the thermodynamic properties of the liquid alloys using the associated solution model; third, to estimate in the framework of the association solution model the degree of chemical short-range ordering; fourth, to predict the composition regions of amorphization using the empirical rule according to which amorphization by quenching proceeds successfully for melts in which the total molar fraction of associates exceeds 0.3 at glass transition temperature. Here presented is a metric projection of our colorimetric cell used for experimental investigation of the enthalpy of mixing in liquid alloys. Some formulas need for calculation the partial mixing enthalpy of metals. Experimental scheme typically used for investigation of the partial enthalpy of metals in case of ternary systems, and the approximation procedure which is needed to process the experimental data. The partial enthalpy mixing of titanium in liquid alloys of this system was investigated at 1873 kelvins along three sections. The scheme for the experiment are shown on this triangle. Experiment start from cobalt nickel alloys with some compositions. The obtained experimental values of partial enthalpy of titanium were shown at figures by circles. These values were fitted by least squares method, and resulting equation is presented. The investigated function has negative values which indicate on a strong interaction of titanium with nickel and cobalt in ternary liquid phase. Obtained functions of the partial enthalpy of titanium were used to calculate the integral mixing enthalpy by integrating Gibbs-Duhem equation along investigated sections. Obtained values were used to describe the integral mixing enthalpy in the entire composition range by the Rayleigh-Gister-Mudjano equation. The negative values of this function primarily result from significant deviation from ideality in cobalt-titanium and nickel-titanium binary system, suggesting that cobalt-titanium and nickel-titanium pair interactions play a dominant role in the energetic of liquid alloy formation. The minimum of the delta MH function is inside the composition triangle near the nickel-titanium system. The significant values of the integral mixing enthalpy observed in the central part of composition triangle indicate a possible good glass forming ability of liquid ternary alloys. This fact allows us to use the associated solution model. In our case, there are two boundary systems with a strong attractive interaction and one binary system with repulsive weak interaction of components. First two systems are described using the ISM model for binary systems. The interaction of the components in the liquid binary AB system is described using the Rayleigh-Gister polynomial. The last term describes the possible ternary interaction. To describe the thermodynamic mixing functions of liquid cobalt nickel titanium alloys within the framework of the associated solution model, we use the data obtained in this work and the parameters that describe interactions in the edging binary systems. The resulting set of ISM parameters are shown in the table. The calculated values of the integral mixing enthalpy agrees well with the experimental values along the investigated sections. According to the model, the minimum of delta MH function is minus 42 kilojoule per mole and are in satisfactory agreement with experimental value. The calculation results at 1873 kelvins indicate negative deviations of the thermodynamic functions of mixing from ideality, which is due to the strong interaction of the components in the melts. At this slide were shown the set of thermodynamic mixing functions for the liquid alloys calculated at 1873 kelvins. The results of calculations at 1273 kelvins and 800 kelvins. It can be seen from this slide that the mixing enthalpy becomes more negative as the temperature decreases. This trend is observed across a broad temperature range, including a region corresponding to both equilibrium and supercooled liquid alloys. The excess mixing enthalpy, mixing Gibbs energy, excess mixing Gibbs energy, and Gibbs energy of mixing of liquid alloys also demonstrate the negative values, and this feature goes more prominent with decreasing temperature. When the glass forming liquid phase is supercooled to the amorphization temperature, the excess Gibbs energy of mixing predominates, which can be related to strong pair interatomic interactions of cobalt titanium and nickel titanium. The next step in our work was to involve representations of the associated solution model to estimate the degree of short range chemical order in metal melts. The associated solution model considers the metal melts as a system of interacting particles in which a chemical equilibrium is established between the monoatomic particles and their associates. The equilibrium composition of the associated solution can be calculated based on the equations of the mass action law, which relate to thermodynamic characteristics of the associates. The total molar fraction of associates can be used as a value characterizing the short range chemical order in melts. The greater is the sum, the greater is the degree of short range chemical order in the melt. According to result of calculations for many binary systems, a high ability to form amorphous phase is characteristic for melts where the composition of the associated solution at amorphization temperature corresponds to the condition where total molar fraction is greater than 0.3 at this temperature. Under conditions of equilibrium existence of liquid cobalt nickel titanium alloys, significant chemical ordering is characteristic, and total molar fraction of associates can reach value greater than 0.5. For supercooled melts, the degree of chemical ordering becomes even greater, and total molar fraction of associates is greater than 0.8. The other lines showing the total content of associates dot 3 at 800 Kelvin deserve special attention and shown at this figure by red lines. In compliance with the empirical rule established by us, these as lines bound the composition range of amorphization by melt quenching. The predicted composition range of amorphization are shown by color fill. This composition range for ternary alloys was not investigated experimentally, but at the same time, the amorphization range of this system predicted in this work successfully generalizes the experimentally known compositions of binary amorphous alloys and opens prospects for conducting further experimental studies in this ternary system. So we can make some conclusions. First, the values of the integral enthalpy of mixing for cobalt nickel titanium liquid alloys is negative and has minimum minus 41 kilojoule per mole. The delta mass function on the whole concentration triangle was described using the Redlich-Kisten-Modiano equation. For the first time, it has been shown that the cobalt titanium and nickel titanium pair interactions play a decisive role in this system, leading to a negative values of the integral mixing enthalpy. Second, the thermodynamic mixing functions of the liquid alloys was modeled in the framework of the associate solution model. This function demonstrates strong negative deviations from ideal mixing, which increase upon cooling of the melts. For equiatomic ternary alloys, the relative contribution to the excess term to the Gibbs energy of mixing increases from 30% at the temperature of equilibrium existence of the liquid phase to 70% at its glass transition temperature. This emphasizes the exceptional role of intensive interaction of components in ensuring the thermodynamic stability of glass-forming liquid alloys. Third, within the ISM framework, the degree of chemical short-range order in the liquid alloys was assessed as total molar fraction of associates. This feature is significant for liquid alloys of the model system and increases with decreasing temperature. The amorphization composition range for the cobalt nickel titanium liquid alloys was predicted based on our previously proposed empirical criterion related with total molar fraction of associates. The predicted range of amorphization is satisfactory agreement with known compositions of amorphous alloys in the H binary systems. Thank you very much for your attention.
Thank you, Dr. Agrawal. Can you hear us? Is okay with the voice? Can you hear us? Dr. Agrawal. Dr. Agrawal.
Yeah, I
The voice is
hear.
okay, yes? The voice is okay? It's okay? Can you hear us?
Yes, I hear.
Okay, so who would like to ask the question to the Dr. Agrawal?
May I put the question from the screen?
Okay, please.
Okay, thank you for a very interesting presentation. And my question is to the beginning of your presentation, say slide number 7. Can you show it, please? Okay, when you speak about ternary interaction, about the necessity to include ternary interaction, yes, and you have the minimum or the enthalpy somewhere in the middle of the system, more close to titanium nickel side. How does it correlate with the phase diagram?
For the phase diagram.
Yes. Maybe there are some ternary compounds, so some ordered binary phases or
Yes,
something like that.
as I know, here's in this place close to the nickel titanium system. This is forms some ternary compounds. I don't say what the type of structure he have, but I know this is a place where tau phase is present and
Okay,
found
thank
on.
you. So you included this ternary interaction because you have known about this phase diagram, or this comes from your optimization or treatment of your results? How did you come to
No,
this
in
decision?
our model we don't use this supposition because to describe successfully in the framework of the associate solution model, we use it only ternary parameters which describe ternary interaction.
Yeah, I see.
No need for including ternary associates. We do not found.
Mhm.
So this result is obtained only due to uh, these parameters, and that obtained model successfully describes all experimental results for the integral enthalpy of mixing
Mhm.
obtained
Thank
in
you.
this work.
Thank you very much. And who would like to more a question? Who would like to ask more questions? Okay, I'll ask. And what are the advantages of your proposed composition for the future appliance in a practice? You said that you have found the composition that it's optimal as a morphization composition. And for the future appliance, what are the advantages of this composition?
Okay, thank you very much for this question. I must stress that experimentally for this system was found only compositions for binary amorphous ALS in agent binary systems as cobalt titanium and nickel titanium. For the ternary system, we do not find any literature data about experimentally obtained compositions of amorphous alloys. We suppose that using a quick quenching of the liquid alloys, we can obtain amorphous alloys in this wide range of compositions, which last from the compositions of titanium from dot 2 to dot 8. Any possible composition in this area, color fill area, uh, according our prediction, is suitable to obtain amorphous alloys.
Okay, thank you. And who would like to ask more questions? Okay.
What is the reason for the decrease in the ability to amorphize when deviating from the given chemical composition of cobalt, nickel, titanium alloys? Thank you.
Please more distinctly to replay this question. I don't hear correctly
The
this
question was
question.
about that if to deviate a little bit from your composition that you have chosen the special one for amorphization. What is the reason of decrease in the ability of amorphization? Why it decreased? If to deviate from the compositions that you have chosen is the best.
We use it our investigation to form multi-component database of thermodynamical parameters for the liquid phase and some of solid solutions as BCC and FCC phases. This database is used in our works to predict possible formation of amorphous alloys in the more multi-component systems which have more components than three components. Uh, So we continue our investigations and find new prospects in further investigations.
Okay, thank you so much. Thank you for your interesting report, Professor Agrawal. And the next one is Ores Dili with a report analysis of the rate of change
Thank
of
you very
stress
much.
density coefficient and the function of different sizes of damaged pipelines. Please, Ores, Ores, the floor is yours.
Yes, I am here, but this work will be present Dr. Gustavo Dominguez.
Okay. Okay. Mr. Domingos Rodriguez,
Yes, I'm here.
the floor is yours.
Yes, okay. Good morning. Can you see my screen?
Yes, we are.
Okay, thank you. Okay, yes, we are from the Center of Research on Corrosion in Mexico and in the University of Campeche. Well, our work is analysis of the rate of change of the stress intensity coefficient as a function of different size of damaged pipelines. Okay, basically what we want is to assess a different propose a parameter to assess difference the damage to compare and to have some kind of control in order to define if some damage is important or is critical or is not critical, basically. So, for example, we have here different structures. The first one is a structure that is damaged because of heat. The second one is damaged because of wear, because it has a lot of oil and is used in oil transportation. The third one is because of chemicals, because you have some kind of corrosion and liquid and going in. And the fourth one, for example, this is because of mechanical wear. You have some kind of crack that is propagating from inside toward the center and from outside toward the center, basically, of this structure. Okay, pretty much what we want is to have a parameter that we are using the name A star. This is we want this parameter to be lower than the A critical that is already specified in the literature. Our idea is that if this parameter is smaller than the A critical, the structure is okay. I mean, the A is basically the size of the crack, pretty much. In this, for example, if we have the crack and is under the A critical, it is okay, basically. We're using this, we're using this lambda, that's basically the stress stress and concentration tensor, and this is the stress concentration tensor, and this is the derivative of the stress concentration tensor. We are using this in order to assess this parameter. Okay? Well, for example, you have two different curves here. And we are assessing this parameter. You have this area where it is okay. I mean, you have a reliable prediction. And pretty much we doing the same thing. We do two different materials for this case. Okay? And you have the same thing here for different for similar structures, but for different material for different damage. I mean, for example, the idea here is to have 2 points in this curve. This is the derivative of the stress concentration tensor, and we plot these derivatives, basically the slopes, right? And in this intersection between two slopes, we have this, we are using this in order to assess this parameter that we want. So we plot, we have these two plots that are intersecting. When those plots are in the point when those plots are intersecting is basically where we have this parameter that we are proposing. Okay, sorry, I can, okay, yeah. So, for example, here, this is the way we are calculating this. You have this derivative. For example, here, you will using this formula. Pretty much what we want is that the derivative is the double of the previous one. We are like walking, if you want to say that, on the curve until we go to another point when the derivative is double the previous one. We continue until the derivative is double than the previous one, right? So we do some kind of medium step here between 1 and 2 and between 2 and 3. We use those points to plot to trace the slopes, and so we have the intersection. Here we are not using A, but A normalized. Pretty much A is the size of the crack, and the G is pretty much the maximum length. For example, if we are considering a crack that is going from the outside to the inside, the thickness will be the G in this case. But for example, if the crack is propagating on the direction of the pipe, pretty much in that case, the G is the length of the pipe, for example. No? Okay, this is the way we assess this parameter. So, for example, here we have some plots, different models with different predictions. The important thing here is to plot, actually to assess, to calculate the A, the curve, and then we use the derivative of that curve, right? So, for example, this is already done. Dr. Ores, Dr. Billy did this. And we are using those for assess. So we have two different curves for two different situations. And this one is inside and outside the thickness of the pipe of the pipeline. And this one is in the center. So you have those two plots. So as you can see, we did the same process that before. So you have this middle point and this middle point, and we are tracing those slopes. You have two intersections, one here and the other one here. So this one is the parameter what we want to assess. We want this to be smaller than the critical one, right? So we are we are obtaining those two parameters. For example, for this curve and for this curve. This is basically the first example of the process. We repeated this same process with different curves. For example, we are changing the position. We have different positions. For example, from the center, this one is closer. This is closer to one. So basically, it's closer to the edge. This one is pretty much in the middle. We have different plots, right? And so we are tracing different values here for each one of those ones. We also did this with very long cracks for different positions. For example, this is closer to this is in the inside. This one is in the center of the structure, and this one is in both sides, outside and inside. Okay. So we also did this. Sorry, we also did this for elliptical damage. We are considering different in aspect ratio of because we have an ellipse, we have an aspect ratio around 55%. So basically, it's slightly longer than the other direction. It's not that much, but we did this for different positions, basically. then we repeat the same process for different aspect ratios, as you can see. For example, this is almost in the opposite direction, and this one is closer in the opposite direction, this one. Okay, we are obtaining different parameters. We repeated this, for example, for damage that is outside the structure. We also did this for damage that is in the center, like this one. This one is exactly inside the tube. It's not approaching neither the center of the outside of the tube, right? And for example, here we are adding a new parameter. That is a parameter that gives the name of the presentation. Basically, this is the radius of the pipe. I normalizing with the thickness that we are studying, right? So we did this for this relationship. We using 3 different aspect ratios. We can see these 3 parameters here. We did this for other aspect ratio. For example, this one is we are considering a very long crack at the outside and a very long crack in the outside of the structure. But here we are assessing the depth of the crack, because the crack basically is considering the whole length of the tube. So our parameter here is how deep it is, basically. For example, we are still with this same relation, this same aspect ratio here. We're changing, for example, we are considering here a very long structure and dot. So basically a small damage. It's not that long. This is what the second one. Okay, you see that those are very similar behaviors. I mean, the parameter is quite similar. It's not so important basically if this is long enough or it's just a dot. You want to say that. We did this for different sorry, we repeated this, and finally we have different ratios because around here. Okay, yeah. And then we repeated the same process for different relationship between the radius of the tube and the damage thicknesses, the thicknesses of the structure. So you have this curve, and we are using the same parameter, basically this relationship, A over G, that we are calling this Z. But it's the same thing, right? So we have this. For example, you can see that here is important because you have a small value here. And we repeat this with different aspect ratios, basically, of the damaged structures for 3 different damage structures, and we are considering a wide spectrum of thicknesses, radiuses. Sorry. We did the same thing here for 3 different aspect ratios. Okay. And finally, our conclusion is that we are considering a proposed indicator of the resistance of the structural elements to crack growth, dependencies of the characteristic value. This is the relationship between the crack size and the thicknesses that we are using. Basically, we are considering this parameter on the ratio, the radius of the pipe correlated to the thicknesses also of the pipe. This is the model we constructed, the pipeline system with cracks defects. We are not considering how those defects are initiated. We are just considering the defects that already exist of various shapes, and we with different size. We are and geometries. So we consider that because of this, the dimension between 30 and 40 is the more critical one. For example, you can see here around 30 is when you have the lower ones. And this proposed approach can serve as a tool for more detailed express analysis, not only for pipelines system, but also for another structural elements that may be encountered in engineering practices. Okay, thank you for your attention.
Thank you very much, Dr. Dominguez. And who can ask the question? Raise your hand, please. Okay, I'm coming.
Greetings, Alex. How does the shape and geometry of a crack line defect affect the change in the stress intensity factor in pipeline system? Thanks.
Sorry, I didn't hear it well.
Okay, I repeat.
Thank you.
How does the shape and geometry of a crack-like defect affect the change in the stress intensity factor in pipeline systems? Thanks.
Okay. Basically, the aspect you're saying that, for example, how change the geometry, the stress concentration tensor is basically that, right? Your question.
Yes.
Okay. Okay. Yeah, this is a thing that the stress concentration tensor was already Dr. Ore's contribution. I don't know, Dr. Ores, if you want to, Dr. Billy, you want to say something about that specific question? Sorry.
No.
Look, okay.
We can move to the next question. Yes?
Okay, yeah, thank you.
Okay. Who will be the next one? Who would like to ask the question? Okay, I'm coming.
I have two questions. Those questions: has the critical defect size been determined exceeding which contributes to rapid destruction?
Sorry.
The question is about the critical defect size. How it determines the parameters, and if you exceeding the critical parameter, what will we do? It will be the pole breaking or something or another. If you exceeding the critical parameter that you have said a lot of times, that you have found a critical parameter, yeah? And if you exceed this parameter, what will happen with the pipeline?
Okay, yeah, okay, thank you. Basically, if the A star is higher than the critical parameter, pretty much what it says is that the structure is not secure for working anymore. Is damaged, so it's not recommended to still be used. Pretty much is the thing. Thank you.
I see. And the next one?
What's the number of cracks and the interaction between them taken into account? Thank you.
Okay, the number of cracks that we are, thank you for your question. Very much, your question is the number of cracks we are considering in each model, right?
Mm-hmm. And what about interaction between them? Have you estimated the interaction between different cracks?
Okay. Pretty much we are just working with one damage at a time in this model. We are not, for example, we are not considering the interaction between different cracks because we have some kind of coalescence of damage, right? No, this is model pretty much is working with one defect at a time.
I see. Maybe it will be in the future, yeah? To the continue of your work. Thank you so much, Dr. Domingos. And the next one?
Thank you to you.
Is Yuri Privachuk. Electrical properties of bismuth, induced stannum, zincum, cuprum, argentum, low temperature solidus. Dr. Plevachuk.
Yes, I'm here.
Okay, the floor is yours.
Just a minute. Okay, can you see my presentation?
Yes, we are.
Okay. So, good morning, everybody. And let me start with my presentation. So the title is As Seen Electrical Properties of Bismuth, Indium, tin, zinc, copper, and silver low temperature alloys. Why we investigated these alloys? So it is not known that the lead-free solder materials now are very important since they just a minute, it disappeared. What happened? No, sorry. Something with internet. Probably now it's okay. Due to restriction of the use of the conventional lead-tin alloys, which contain toxic lead, so numerous laboratories are now involved in researching of different various lead-free solders, which have similar properties. But the problem is that there is not, unfortunately, the single alloy, which is similar to the excellent characteristics of tin lead. And that is why the requirements for such alloys, they should have low melting point, they should have good mechanical properties, and also satisfactory electrical properties, electrical conductivity or electrical resistivity. And modification of different binary and ternary alloys, now this is one of the main problem and main task, which is carried out the experiments in different laboratories. It is known that very popular is now the alloy, the lead-free alloy, which compose of these three elements: tin, silver, and copper, but they still have a rather high melting temperature.
I'm sorry, I could interrupt you. It's an ARAM, it's a warning for Dnipro. Right now, it's a red status, and we would like to propose, if somebody would like, you can go to the shelter downstairs, or you can continue our discussion and our conference. But I need to say to you. So I apologize. You can continue.
I can continue? Okay. Thank you. So, but at this point, there was a decision to add additional elements to this binary and ternary alloys, which are already known. One of these additional elements could be bismuth, could be indium, also could be zinc, and for example, the increase of diversity of electronics, which is now developed, like soft electronics, biomedical devices, or solar cell, the melting temperature should be even smaller. And for example, for some biomedical equipment, the melting temperature should be below 100 degrees. And that is why we investigated these alloys, which are multi-component alloys, and also they are high entropy alloys, because these alloys are consist in the elements of equiatomic composition. There is 4, 5, and 6 different elements which are in this alloys. So we investigated the resistivity and also in the range between the room temperature and the melting solidification range. And we also analyzed these results with DSC and X-ray. So the samples were produced in the form of ribbons. And here I will show you how it works. Yes, we have the ribbons of about 6 millimeters of width, and the thickness was about 100-120 micrometers. This is a planar casting procedure, which is in principle well known. The electrical resistivity was measured by a 4-probe method during heating and cooling with the rate of 10 Kelvin per minute, and also the melting solidification range we also analyzed by DSC with the same rate, and also the crystallographic analysis was performed by X-ray methods. Finally, we received very interesting curves, because if we have a look at this heating rate and cooling curves, we see that the resistivity in the solid state, this is approximately from the room temperature to up to this region, it increases with heating as predicted. But this increase is not gradual. And we see that the heating, the curves, the heating curves are not smooth. Here we can find the onset is about the 83 Kelvin, but then we have one kink at a little bit higher temperature. Probably this kink is connected with the reaching of critical concentration of the crystalline phase. Here we have a melting, which reflects another inflection, and also then the resistivity increased gradually in the liquid state. This melting, and when we start cooling, here we have some hysteresis, and this is the cooling temperature, and the cooling is accompanied by gradual decrease of resistivity, but at some region it becomes more drastic. So the melting and the solidification, as I told, they form the hysteresis, and it is indicated as an existence of certain melting and solidification temperature range. The 5-component alloys, to these alloys we added also copper. We can see also the curves are not smooth, and already at about 58 degrees, we have some phase transformation in the solid phase. The onset of melting is practically similar to the previous alloy, and also this structure transformation, it could be considered as evidence by another inflection in the heating curves. Finally, we have the transition to the liquid state also, and cooling also is accompanied by a gradual decrease, which later becomes more drastic. So it is quite more or less similar. And finally, the third 6-component alloys, it also show the very similar behavior. And it was, as I told, in contrast to binary and ternary alloys, it was not so predictable as we expected. Then we make the experimental analysis by the DSC, and from DSC we found the melting temperatures, the peak temperatures, and also the difference between the melting and solidification temperature. And we should say that this range is not stable because it depends on the cooling rate. So, and also we could investigate the temperature, the resistivity values at room temperature. Finally, in order to explain why such peculiarities occurs in these curves, we carried out the XRD analysis, and the analysis revealed that there are several compounds. Mostly this is bismuth indium, and here tin bismuth. Here we have also copper 5 zinc 8, but this bismuth indium was found in all 3 cases, in all 3. Here we have also the additional compound, bismuth 3 indium 5. And In order to make some explanations, what is going on, what happens during this heating and melting and then the solidification, we analyze different phase diagrams. This is only some of them. When we have a look at these phase diagrams, we can see that some...
We cannot see the phase diagram. I'm sorry. We just see the first slide. Could you repeat your presentation? Reshare
it. So it doesn't change?
No, it doesn't change. I'm sorry. You said
Here
about ternary diagram, but we couldn't see it.
Maybe just a minute.
Please try to close the presentation and try again to share the screen.
Okay, maybe I will try. And now.
Yes, and now try to share screen.
Okay, once again, yeah. Why it doesn't work? Yes, I have the presentation. Is it visible now?
Yes, and now please start slideshow.
But where it was interrupted?
It's not full screen. We don't see full screen. We see your presentation, but not in full screen. Or F5. 5.
This one?
Okay. Please try to change slides. We will check. No, it doesn't work.
But strange, because I see everything. It changes.
But it doesn't change in our screen.
Yeah, everything is changed. It's okay.
Dear Professor Yuri Plevachuk, do you translate full screen or window? Oh, it's changed.
Now it changed?
Yes.
But now it's not. But now it's not full screen. Okay. Yeah, I will change maybe.
Not full screen, but we can see.
Okay. So start from. Maybe I will repeat from which side. Slide.
Okay. Thank you.
So have you seen already this slide?
You can choose the place from every you would like to start. You have finished the ternary diagram, but we haven't seen the previous slides too, as I understand.
Okay, so I wanted to say, okay, shortly, in order to understand what happens during this heating, cooling, and which phase transformation have place, we make the XRD analysis. And we found in this, according to this analysis, that there are some compounds, for example, bismuth, indium, copper, zinc, and also here also copper, zinc, bismuth, indium in different proportions. And we wanted to have a look, understand which composition, which compound plays the most important role in this transformation. So that is why we analyzed different diagrams, and we found that some of them are simple, some of them are very complicated, and that is why probably this is the reason of this transformations. The most interesting is probably bismuth indium, because all this bismuth indium in like eutectic, like also, for example, bismuth 3 indium 5, they play the most important role in this transformations. And certainly this inflections on the curves in the range between beginning and the end of melting are associated with different compounds, probably also with bismuth 3 indium 5. But we cannot say that this is only their influence. Probably the influence of other possible phases could be also play the role, but it should be, the next experiment should be done in this case. When we compare all these resistivities for all three compositions, all three this multi-component alloys, so we can say that they are higher than tin lead, which is about 14, and also higher than the so-called SAC alloys. But in principle, it can be used, it can be considered as the lead-free alloys. But we should also investigate, we should know the mechanical properties. And this is also very important, because when we see how there is a change during the solder joints, there occurs different growth of intermetallic compounds, especially this is copper 3 tin and copper 6 tin 5. And what is the advantage of this many component alloys? When they form some small compounds, these compounds can suppress the growth of intermetallics, of these two intermetallics. And this analysis were done after, for example, at room temperature, after 4 months aging at -20 temperatures, because we should know how it will, the behavior in different temperature ranges. This we see, this is before and after the aging, and we see when these intermetallic compounds will grow from one substrate to another substrate, which are probably, this is two details which are connected with this joint. In this case, this solder joint can be broken, and it would be not so good. Finally, we go to the conclusions that the resistivity of this multi-component alloys depends of composition. There are some anomalies, and also the formation of intermetallic compounds affects abrupt increase and decrease of resistivity. So, but certainly the information about microstructure and mechanical properties is very important, and these investigations are now in progress. And from the scientific point of view, how to explain this? We think this similar behavior was observed before in tin-containing smells, and it was explained by the assumption, our assumption, that the molten metal undergoes several structure transformation, because at the beginning it is micro-heterogeneous, and after melting, and it goes to the true solution, to the homogeneous state. And also the anomalous temperature dependence of some properties is associated with the structure transitions of short-range orders. And during these transitions, the previous bonds are broken and the new bonds are formed, and becomes a more disordered high temperature liquid. So this is all my presentation. Sorry for these problems. I don't know what happened, but anyway, thank you for your attention.
Thank you very much. And who would like to answer the question? Dear colleagues, please raise your hand. Okay, I'm coming. Thank you very much for your very interesting presentation. And as a result of your presentation, I have one question in regard to the way how the change in the chemical composition of the solder can affect corrosion and cavity formation. Thank you.
What about corrosion? Sorry, can you repeat? Because
how the chemical composition of the solder can affect corrosion, and the cavity formation.
Yes, this is a problem. Especially this is a problem of these cavities, the so-called Kirkendall voids. And we investigated this. Probably here is seen in one. You mean here? We investigated the solders without any additions and also with additions, and certainly we also could measure the percent of porosity which is connected with these voids, and it was about maybe 10–11%. About the corrosion, it's difficult to say. We did not investigate such properties, but but about voids, yes, we have a lot of results with these voids, and we try by different methods to avoid them.
Thank you so much. Who would like to answer the question more? Okay, I'm coming.
What way does the introduction of additional elements, copper and argentum, into your alloys affect the electrical resistance and structural stability? Thank you.
And, as I understand, you ask why we add also the silver, argentum.
Yes, and how do they influence on the electrical resistance and stability?
Yes, the matter is that in these alloys, usually we started from the assumption that the most details and the most, as we say, substrate, they are from copper and also silver. Silver appears like, for example, it makes some compounds like here silver-3 tin, and we started from our main solders, which are SAC, stannum, argentum, cuprum, and in this case we have this silver, but very small proportion. Why we put maybe so big proportion to this alloys, like about 10? Because we also tried to investigate how it will work as a high entropy alloys. There is a lot of questions why high entropy, because high entropy from one idea, they should form only one phase, but here there's also multi-phase high entropy alloys, and in principle we did not see any I will have a look. So the addition of silver, we can see here, is increase the resistivity in this case. But probably we cannot say that this is only resistivity connected with the amount of silver, because there could be so many intermetallic compounds in this alloy that we cannot predict which element gives them more influence on the electrical resistivity.
Okay, I see. Thank you so much. And the next question maybe will be mine. You have soldiers with a lot of components, and the soldiers are not homogeneous, as I understand. Does it affect on the properties of these soldiers? And would you recommend some ways how to make it more homogeneous?
Probably after investigations of such many component alloys, this probably is also mostly scientific work, because we know that any industry doesn't like to work with the alloys which contain more than 3 components. So in this case, probably it's not possible to avoid formation of all these compounds, and it's also very difficult to make it homogeneous. But as it was such idea, so we tried to investigate this. But we can see, we can predict. The main idea was to have a look how these compounds which forms, how these phases can suppress the growth of these intermetallic compounds like between copper and tin.
Thank you so much. Thank you very much, Dr. Plevachuk, for your interesting report. And this was the last report before coffee break. Right now, I'm announcing the coffee break time. Dear colleagues, please, you have a rest 10 minutes. After 10 minutes, at 11:10, I'm sorry, at 11:30. At 11:30, I'm waiting for you here in auditorium and online. So you have 20 minutes to have a rest, dear colleagues. Dear colleagues, could we continue? Dear colleagues, could you hear me? We are ready in our auditory. We are ready to continue. Steve, can you hear us? Steve, can you hear us? Dear colleagues, is the voice okay? Can you hear me? Please ask anybody, can you hear me?
Yes, we hear.
Thank you so much. So could we continue? Could we start now again our conference? Are you ready? Are you ready to continue? Is the Dr. Singh ready? Because he will be the next one. Dr. Singh.
Maybe we can start with our next presenter, and then we can try again.
Okay, so we can skip right now Dr. Singh, yes, his speech, and move a little bit further. Am I right? Because Dr. Singh is not online, we couldn't see him.
Olena Prilipko, yes?
Is Olena Prolipka here?
No, okay, next presenter.
Is Alexandra Tolochina here?
Yes, I'm here.
Okay, so we can start with you. Is it okay?
Okay.
Okay,
One
so
moment,
we are continue our discussion and our conference, and the first one will be Alexandra Tolochina, Ferrum 28 best Aries, produced via direct powder forging technology. Please, the floor is yours.
Thank you very much. One moment. I share my screen. Do you see my presentation?
Yes, we are.
Okay. Good morning, dear colleagues. I'm very pleased to be at HighMatTech-2025. And today I'll be presenting our recent study carried out together with my colleagues entitled Iron Aluminium Based Alloys Produced by Direct Powder Forging Technology. Our research focuses on the development of intermetallics materials that combine high strengths at room temperature with excellent heat resistance and grip stability up to 700 degrees Celsius. So before I go into details, let me briefly outline the structure of my presentation. First, I discuss the introduction of these materials, Then I'll focus on the approach to improving the heat resistance, followed by an overview of direct powder forging, DPF technology. And next, I'll present some experimental results for iron aluminium, as well as its modified versions with metals and oxidation additions. Finally, I'll summarize the key conclusions and perspectives for further development. Iron aluminide intermetallics alloys have attracted considerable attention due to their unique combination of low density, excellent oxidation and sulfidation resistance, and good strength retention at elevated temperature. Compared to traditional stainless steels and nickel-based alloys, these alloys offer a much lower material cost, first of all, and reduce environmental impact while maintaining reliable mechanical performance up to 800 degrees. However, these materials are brittle at room temperature, and their plasticity strongly depends on grain size, composition, and processing rules. In recent years, advances in powder metallurgy and deformation-based processing methods, such as DPF method, have opened new possibilities for overcoming these limitations by refining microstructure and enhancing ductility and toughness. So, because of their combination of oxidation resistance, creep strength, and low density, these materials are being considered for a wide range of high-temperature structural applications. These include components in energy systems such as turbine blades, heat exchangers, as well as parts in chemical and transport engineering, where corrosion and temperature stability are critical. In addition, dispersion strengthened and composite forms of these alloys reinforced with borides or carbides show promise for uses in next generation power plants and gas turbines. The most important challenge is significantly improve creep resistance, which requires a combination of strengthening mechanism. For example, grain refinement, rational microalloying, and dispersion strengthening, either through in situ formation of ultrafine particles during thermomechanical processing, or by adding them directly at the starting initial powder mixture. Powder metallurgy methods are particularly well suited for this purpose. The direct powder forging DPF method enables the production of finished components in a single technological cycle. Unlike the classical DPF approach, which use pre-alloyed powders, our work proposes innovative powder metallurgy route to obtain iron aluminides directly from a mixture of elemental iron and aluminium powders. This technique allows shaping of the component already at the stage of cold pressing, using ductile iron and aluminium. Low temperature strength and strain handling are enhanced through structure refinement during intensive milling of powders and subsequent high temperature deformation processing. So in this slide, I want to show you DPF technological scheme. The powder mixture was sealed in a steel container and compacted under argon atmosphere. Then hermetic capsules were heated at to forging temperature, and then hot forged on a screw press at different temperatures. After forging, part of the samples was analyzed directly, and the rest were vacuum annealed at 1,300 degrees to achieve full densification. And after that, the set of mechanical properties was determined at room and elevated temperatures. For binary iron aluminum alloys, we have studied these aspects in a series of work. I mean, effective implementation structural modification requires us optimization of DPF processing parameters. And special attention was given to the structural sensitivity of mechanical properties at room and elevated temperatures. The obtained single-phase intermetallic alloys demonstrate high strength at low temperatures, while its creep resistance approaches that of stainless steels. Even under optimal thermokinetic conditions of deformation, the sample showed a tendency toward interparticle fracture and negatively affecting crack resistance. At triple junctions of powder particles, planar defects remained and serving as nucleation sites for brittle cracks. To overcome these shortcomings, we introduce an additional annealing stage. This treatment promotes recrystallization of interparticles boundaries, reducing interparticle fracture. Planar defects lost their sharpness and transformed into spherical pores. As a result, low temperature strength and fracture toughness improved. Further refinement of high temperature densification requires a technological scheme that enables recrystallization of interparticles boundaries directly during deformation, but at lower temperatures. Such structural changes can be achieved through the mechanism of dynamic recrystallization, DRX mechanism. It's also important to note that the initial stage, I mean the densification stage, the porous sample undergoes plastic deformation that far exceeds their threshold for dynamic recrystallization. But at this stage, only the formation of interparticles boundary defects occurs without their subsequent recrystallization. In this slide, I'd like to highlight the dynamic recrystallization conditions for iron aluminum based alloys. We found that recrystallization can occur with a wide range of strain rates and temperatures, typically during rolling or rotary forging. This the critical strain is about 15 to 30%, and the expected temperature window for full recrystallization is around 1200 degrees Celsius. Improvement of high temperature properties can also be achieved by rational macroalloying with elements that show down diffusion processes, thereby enhancing creep resistance. In our studies, we demonstrated that, for example, molybdenum additions increase creep strength up to 750 degree. Further enhancement of properties is associated with the implementation of dispersion strengthening. In the direct powder forging, high temperature strength is achieved either through the in situ formation of ultrafine particles during thermomechanical processing, or by their intentional introduction into the initial mixture. At room temperature, the dominant contribution of strengthening comes from structural factors, namely grain refinement. But according to the whole patch model, a grain size of 2.5 micrometers corresponds to approximately 500 megapascals, while a grain size of 5 micrometers contributes about 300 megapascals. The strengthening from fine second phase particles estimated by the ORA1 model is 200 megapascals. And for iron aluminides, lattice fraction must also be taken into account, with contribution around 400 megapascals. Considering these parameters and applying the Cox additive principle, the calculated total yield strength at room temperature is close to the experimental values. Those at room temperature dispersion particles are not the primary strengthening factor. However, the elevated temperatures of 750, the situation changes dramatically. Grain boundaries lose their role as effective barriers to plastic deformation due to accelerated diffusion along boundaries, Cobble mechanism. And lattice friction also weakens as a result of cross slip and vacancy mediate mass transport. In this regime, incoherent particles become the dominant source of high temperature strengthening and providing keep resistance up to about 0.7 melting temperature. In the optimal structure state, materials demonstrate high creep resistance, and a drawback of the in situ approach, however, is a relatively large particle size, around 200 nanometers, which tends to coarsen during subsequent high temperature annealing. And in summary, the developed powder metallurgy route allows the production of iron aluminum based intermetallic composites with excellent low temperature strength, high creep resistance, and thermal stability up to 750 degrees. And the combined mechanism of microalloying and oxide reinforcement proved particularly effective in surprise and diffusion controlled softening and ensuring outstanding long-term performance. So we are gratefully acknowledge the financial support provided by the National Research Foundation of Ukraine, which made this study possible. Thank you very much for your attention.
Thank you very much, Oksana Tolochina. And what about questions, dear colleagues? Who would like to answer the question? Please raise your hands, and I'm coming to you. Who will answer? Okay, maybe I'll answer. Could you say us what about the scalability of your technology? You, as I understand, you have produced small specimens, and is it scalable for industry process?
That's a great question. Thank you very much. Now, it's definitely something we plan for industry production, but now we just have only a small size experimental samples.
Thank you. And who would like to answer?
I have a small question. Yes?
Yes, please.
Could you tell me about first principle calculations? Where is?
What do you mean, first principle calculation? About strengthening?
Yes.
It's
very interesting for me because this is very complex calculations. How much atoms in unit cells and others? We can me informating about this? No.
About this, no. I can add about the strengthening mechanism because we are occur research about complex impact of strengthening mechanism. For example, at the room temperature, we use refinement process, and then we change the strengthening mechanism like dispersion strengthening, hardening, like that.
Mm-hmm. Yes. Yeah, of course. You used our potential mechanism and our machine or others. I was stuck. This is seems to me that you use foreign machine potential, yes?
No, we just use our equipment. If I
Our
understand you
equipment?
correctly.
Ukrainian
Yes,
equipment?
yes, of course, it's only Ukrainian equipment.
Where?
In Fransevich Institute for
Oh!
Material Science.
It's great. Thank you.
Yeah, it's a process hot forging.
Thank you.
Thank you too.
Thank you.
I have a question. What physical and mechanical mechanism allows the proposed method increasing the complex of alloy properties?
Sorry, I very weak hear you. Could you please repeat?
What physical and mechanical mechanism allow to the proposed method increasing the complex of alloy properties?
Thank you very much. It's a complex of mechanism, like I showed you before. First of all, it's we achieve it. First of all, grain refinement. Then we propose rational microalloying, like adding some metals, for example, molybdenum, niobium, nickel, titanium, and of course, it's is it all? And oxidation particles.
Thank you so much. Thank you very much for interesting report, Ms. Tolochina. And I would like to ask if the Professor Sink and Professor Ramazani online, could we move back and hear invited speakers or not? Professor Sink, Professor Ramazani, no online. Okay, and I'll ask, is Olena Prilipko online? Olena Prilipko is online. No? Okay, so we move on. And the next one is Igor Protokvilov, new electroslag technology for producing manganese-containing titanium alloys. Is Igor Protokvilov online?
Yes, I am online.
Okay, Dr. Protokvilov, the floor is yours.
Just a second. Could you see my presentation?
No, right now, no. We don't see anything about instead of you. We just see you.
And now?
Just you. Now your presentation.
I'm sorry, something wrong with my computer.
Don't worry, you could manage it, I know. Try to share.
Sorry, maybe the next speaker made presentation. I couldn't show my presentation, unfortunately.
You just share your screen, open your presentation, and then share your screen. Yes?
Yes, no, by something wrong, something.
Because we can see you, it means that we can see your presentation. Combination of Alt and Tab. You can press button Alt and Tab.
Yes, I use this. And now you can see something.
Just you. You need to open the presentation at first, yes? And then
Yes, I open the presentation and then but could you give me permission to? Okay, I'm sorry, I haven't changed the computer, maybe something.
Okay, so the next, we can move a little bit next, yes, and then we will back to you, okay? After the next speaker, we will back to you. Is it okay? Okay, so the next one is my turn. Tatiana Golub from Ireland Steel Institute. Dear colleagues and auditory, can you see my presentation? Can you see? Is it okay? Could you tell me somebody, is it okay? Can you see the presentation online?
Виталик, можешь подойти? У меня не сработал компьютер, чтобы стоило его включить.
Dear colleagues, Can you see my presentation online? Is it okay?
No.
Could somebody tell me?
No, we can see.
And right now, can you see my presentation?
We can see your screen in the room, but we can see the presentations online.
I see.
We can see your room, we can see you and your screen near you, but we can see presentation in online mode.
I understand. We will try to change it. Oh, and what about now? Does something change? No? No. Началось? Is it okay? I'm sorry for this technical moments. This one, mine. Вот это моя. This one.
Our technical team suggested to do the usual presentation to... Yes, currently it's okay.
Oh, fine. Thank you so much, and I am apologizing for this technical moments. Please, thank you for your passion. So I can start. I'm Tatiana Golub from Iron and Steel Institute, senior researcher, and the topic of my presentation is investigation of the multi-streamer spark discharge impact on the solubility of gaseous nitrogen at iron carbon melt. In recent years, the industrial production of steel products with certain amount of nitrogen for energy, transport, medical and pharmaceutical industries has increased. There are two ways of alloying this nitrogen, using in a solid state nitrogen containing ferroalloys or purging this nitrogen. The first one is most widespread, but production of such ferroalloys needs a lot of costs, and they have a harmful effect on an environment, its storage, transportation, production, and use. So why the use of nitrogen in gaseous state is much more environmentally friendly for us, an attractive process. But as we know, the solubility of gaseous nitrogen in a melt is quite low, and the highest level is restricted. The next slide, please. There are different ways to activate nitrogen dissolution in iron carbon melts. Among them, pressure increasing, temperature increasing, addition of nitrogen forming elements, and electrical activation. The last one occupies a special place. There are different ways to make an electrical activation. First of all, it would be plasma, like plasma ion nitrogen during the treatment of solid metal parts, or ion plasma arc melting. Both of them need special conditions for vacuum. And there are different types of electrical discharges: electrical arc discharge and electrical spark discharge. First of them is independent gas discharge that doesn't need a special pressure requirements, and its power is quite high. It's about 80 watts per kilogram. And then next one is spark discharge. It's not stationary type of electrical discharge in a gas that occurs at room pressure. And it has much lower power than arc discharge. As a result of passage of current during this type of discharge, you can hear the special sound, the crack sound. It appears since the passage of this current leads to the formation of shock wave in front of it, with increasing the pressure and temperature in the ambient atmosphere. By this way, it could influence on the nitrogen flow. As we assumed, it would separate molecules to the atoms, nitrogen molecules to the nitrogen atoms. The next slide, please. So we have chosen electrical spark discharge to investigate how it influences on the dissolution of gaseous nitrogen in iron carbon melt. The base of it was calculation of Gibbs-free energy of nitrogen dissolution processes from two reactions in molecular state, right hand, and from atomic state, left hand. And you can see the dissolution of nitrogen from atomic state is reasonable. It has a very low level of Gibbs energy. So we could assume that our influence on the nitrogen flow could enhance its solubility in iron carbon melt. To assume that our laboratory scale equipment has a very small amount, it's only 1 kilogram induction furnace, we should choose such charge to obtain the result in a short blown period. So we have checked the relation between nitrogen content and carbon content as a main component of steel. And you can see that the higher level of nitrogen could be obtained with a lower level of carbon. So we have chosen low carbon steel for our experiment, and without any special additions, to estimate just only the influence of an electrical spark discharge on the solubility of gaseous nitrogen. The next slide, please. The experiments were done, high temperature experiments were done on laboratory scale model. The base of it is 1 kilogram induction furnace that was adjusted with a superstructure on the top that holds two graphite electrodes producing discharge, electrical spark discharge. Discharge was produced with multi-streamer and single streamer regime. So it was adjusted to the source of power with 30 kilowatts voltage. The purging was done through the top, through the funnel in this superstructure, to the metal melt, melted in a crucible in an induction furnace. Different treatments were done. First of all, purging with pure nitrogen without any influence, then purging with nitrogen activated by spark discharge one streamer and multi-streamer type. And then for comparison, blowing were done with argon with the same blowing period. And again, for comparison, we just holding the metal melt during 1.5 minutes. It was the same period that we purged with the nitrogen. After every blowing, we took the metal sample for the analysis. Every treatment was done 3 times, and then we averaged the results. Show please the next slide. The averaging results we obtained shown on this slide. After just holding the metal melt in a crucible, we have noted that no changes in the metal composition was registered. After the blowing with argon, pure argon, we have noted that main composition have not changed, and just a little bit changing in nitrogen content was observed, just a little bit negligible. After the purging with nitrogen, this same pure nitrogen, this same now changing in approximately now changing in main metal composition was observed, but the increase, it was observed the increase in nitrogen content in 5 times. After the purging with activated nitrogen, activated by one streamer and multi-streamer discharge, we have noted increasing in oxidation of main components, carbon, manganese, and silicon. And we have noted the much more higher increasing of nitrogen content by 6 times during the one streamer discharge using, and by 9 times after multi-streamer discharge using. If to say about changing in main components, we suppose that all the blowing technical parameters and conditions were the same during the all our treatments we have done. So we thought that during the appearing of the electrical spark discharge in an open atmosphere, it must influence on an oxygen in atmosphere, this formation and ozone that could be flowed to the metal to estimate if it forms, I mean if the ozone forms and what is the level. The special experiments were done. Please show the next slide. You can see the laboratory benches that we used. We have checked 2 types of laboratory. We have made 2 tests in an open atmosphere. So we took the same as we used substructure with the same electrodes, the same source power, everything the same. And the outlet of the substructure that we used, we checked if the ozone occurs with ozone matter cyclone 5.0. And the same experiment we have done without atmosphere in a sealed vessel that was filled with nitrogen before the experiment. And we have found that after the appearing of spark discharge, the ozone about 1 milligram per meter cubic concentration was registered at the distance from the discharge about 60 millimeters. This distance was the level placement during the hot metal experiments. So the ozone could influence on the metal melt quite well. And if to say about the influence electrical discharge on the increase of nitrogen content in iron carbon melt, we have done the special experiments, more tests. First of all, we have checked if the discharge influence through the temperature increase in a gas flow. In an outlet of the superstructure, through we have done the purging, we measured the temperature, and we have recognized that the temperature change was negligible, about 30 degrees, not more. So it couldn't influence on the separation of molecules of nitrogen to the atoms. We move to the next way how to this type of discharge could influence on the gas flow, and we have measured ion current with Langmuir method. We have placed 2 electrodes at the outlet of superstructure. Through we have done the purging and measured ion current strength. And show the next slide, please. And we have found that during the electrical spark discharge, multi-streamer and single streamer, as in open atmosphere and without an atmosphere, we have found, have registered positively and negatively charged particles. The share of positively particles 5 to 20 times was higher, and these particles moved through the current flow to the level of metal melt. L is the level of metal melt at high temperature experiments. And we have found that in an open atmosphere with the presence of an oxygen, the level of such charged particles was higher, approximately 2 times than without it. So we could assume that during the influence of electrical spark discharge on the nitrogen flow, it affects on it with the separation of nitrogen molecules to the atoms and then ions with positively and negatively charged particles. And assume the available in literature information, we could propose the perhaps mechanism of influence of such a discharge on dissolution of nitrogen. As we found in literature, if the positively charged particles of nitrogen ions common with electrons, it's very special moment that we need an electrons in this process, could form the nitrates of ferron. So why it could enhance the solubility. You can see the reaction of formation of nitrogen nitrates, ferron nitrates. This reaction that are shown on the slide has very low Gibbs energy at the temperatures of steelmaking processes. So they could explain our enhance or the solubility of nitrogen. In the next slide, please. And we have done comparison of obtained our results with other treatments, other treatments that use nitrogen purging at pressure, ambient pressure, without special conditions, without vacuum or without elevated pressure. And we have found that our results are on a presentative level. So we obtained the results that at the level of microalloyed nitrogen skills. So the next slide, please. So our high temperature and stand benches, laboratory benches investigations could assume that electrical activation could increase nitrogen gas solubility at one streamer discharge type by 6 times, and after the multi-streamer impact by 9 times. And we have found that ozone forms during this process that could influence to the metal melt. About 1 milligram per meter cubic we have registered at the level of 60 millimeters from the discharge. We have found that temperature increasing during the electrical discharge is not the way that it's influenced on the gaseous nitrogen, and the main reason that it's influenced is separation of molecules to the ions, positively and negatively charged particles we have registered by the Lindner method at the representative level, and so we can propose the mechanism of its influence. So the formation of positively and negatively charged particles in nitrogen gaseous flow and its dissolution in metal melt produces ferron nitrides that has negatively very low negative Gibbs energy, as we recognize. So we could say that the method that we just started to study, it's quite promising, because after a very short period of blowing, without additional special components that make nitrides, have obtained the result of nitrogen increase in metal melt at the level of microalloyed melts. So we just think that we need to continue these experiments and to make it in a bigger, to scalable it. Thank you very much. And who has a question?
Dear Tatiana, thanks for your interesting report. I have some questions to you. And first of them is how did single stream and multi-stream discharge differ, and how did you control them?
Thank you so much. As you know, spark discharge, it's a streamer formation discharge. Could you show the slide streamers a little bit higher? The third one. The third, please. Oh, sorry, no, please, the 5. This one. You can see the one streamer and multi-streamer discharges. Both of them occurs at the same electrical potential, but at the position of electrodes, the close position of the electrodes, we could form only appearance, could form only one stream, so appearance only one stream charge is reasonable for this one position. And if you move it a little bit, and the distance between the electrodes will be higher, we could say that the multi-streamer discharge appears. And as we found that this one is better for influence from the position of influence on the nitrogen. So distance between the electrodes is the main reason how to control it.
Thanks for your answer. And second, my question is, why was it necessary to use graphite electrodes to create discharge?
Yes, we have checked different types of electrodes. Graphite is cheaper, but if to use steel electrodes, and as we said, the ozone occurs. This ozone could influence with the electrodes, and electrodes cover, steel electrodes cover with oxide layer, and it interrupts the stability of the charge. So why the graphite electrodes we have chosen, they have not covered with the oxide level, and the stable discharge could occur.
Thank you very much.
Thank you for your question.
I have a question.
Thank you.
If it was established that under the action of a spark discharge ozone is formed, which affects the oxidation of melt components, how can such a discharge be used for metal processing?
Yes, the ozone formation is not reasonable in our recent investigation. I agree with you because it could influence on the material, and we have a proposal for this. We need to use a controlled atmosphere, like for example in an older furnace we have a lid, so very small amount of an atmosphere inside the vessel, so just very small amount ozone will form, and no flow of free atmosphere, free air to the process will influence. So we need a controlled unit with a lid. Thank you. Thank you very much. Thank you for your attention. And we can move further.
Thank you, Mr. Tianago, for your interesting report.
I would like to ask if the Dr. Singh or Dr. Ramazani here, could we hear the invited speakers? No? Dr. Ramazani, Dr. Singh, Dr. Ramazani, Dr. Singh, no? And I would like to ask Olena Prilipko, are you here? Olena Prilipko?
Dear Professor Tatiana, Olena Prilipko is not available now to present their presentation, but maybe Igor Protokovilov can share screen and make presentation. Igor Protokovilov, are you with us?
Yes, I am here. I start to demonstrate my screen.
Okay, Dr. Protokolov did a report new electroslag technology for producing manganese-containing titanium alloys.
Could you see my presentation?
Yes, we can see your presentation. Oh, yes, it's okay.
Try to change the slide for any case.
Okay. Dear colleagues, my name is Igor Protokolov. I'm from Paton Electric Welding Institute, Kyiv, Ukraine, and title of my presentation is New Electroslag Technology for Producing Manganese-Containing Titanium Alloys. As you know, most titanium alloys contain alpha and beta stabilizers, which improve the properties of titanium. Regarding beta stabilizers, vanadium and molybdenum are mainly used. But manganese is also a strong stabilizer for titanium. But unlike vanadium and molybdenum, manganese has some advantages. First of all, manganese is widely available and low-cost material. In addition, manganese has good biocompatibility and has a low melting point. So it could be effective alternative to costly vanadium and molybdenum, but there is a problem. Manganese has a high vapor pressure. This graph shows the vapor pressure for titanium and some alloying elements used for titanium. As you can see, the vapor pressure of manganese is about 20 times higher than, for example, aluminium has. So such high vapor pressure of manganese contribute to evaporation of manganese during melting of alloy using traditional vacuum methods such as vacuum arc melting, electron beam melting, or vacuum induction melting. In addition, manganese tends to segregate in titanium alloy. So the problem is evaporation of manganese during melting process and its tendency to segregate complicates the production of titanium alloys with a given content and uniform distribution of manganese. Promising method for production titanium alloys with a high vapor pressure element is the technology of magnetically controlled electroslag melting developed at Paton Welding Institute. In this process, the melting of consumable electrode made of initial raw materials is carried out in a chamber-type furnace. The melting space is first evacuated and then filled with an inert gas. So the melting process is realized under the overpressure of inert gas. The source of heat energy in this process is a Joule heat, which is generated in the slag pool when the electric current is passed through it. The ingot is formed in a copper water-colored mold by sequential solidification of the liquid metal pool. And an important characteristic of this process is that we use an external magnetic field formed by this solenoid for steering the liquid metal pool to improve the homogeneity of the ingot metal. So the key features of this process is non-concentrated heat source, which is slag pool, inert gas overpressure, the fact that the slag pool is covers the liquid metal pool, and the steering of the liquid metal pool. And these key features contribute to absence of evaporation of alloying element during melting process and contribute to chemical homogeneity of the resulting metal. So these key features show the potential of this process to produce manganese-containing titanium alloys. This slide shows the principle of electromagnetic influence during MEM process. This principle is based on interaction of an external magnetic field with melting current. This current passes through the liquid slag and liquid metal, and as a result of the interaction of magnetic field with melting current, the electromagnetic force are formed in the liquid metal and slag pool, and this force influence the hydrodynamic situation in the slag and metal pool. We use the pulsed magnetic field, and this allows us to create vibration of the melt and create the electrovertical flows of the melt. And this allows us to influence the main metallurgical process during melting, such as melting of consumable electrode, transfer of electrode metal, and solidification. This slide illustrates the influence of the external magnetic field on the metal droplet transfer during melting process. This is the result of physical simulation for different value of external magnetic field induction. As you can see, the magnetic field can significantly influence the metal trajectory and metal transfer during melting process. This is the real-time playback for this value of induction of magnetic field. As you can see, magnetic field significantly influence the trajectory of the droplet. Allow us to influence the size of the droplet, the time of the existence of the droplet, I mean the time of the transfer through the slag pool, and the place where the droplet fall into the surface of the liquid metal pool. This slide shows the view of the setup for MEM process and technical specification of the setup. This setup allows us to produce ingot with a diameter up to 250 millimeters. So the aim of this particular research was to investigate the features of producing manganese-containing titanium alloys using the magnetically controlled electrostatic melting method and to investigate the properties of the resulting metal. The object of the research was the OT4 alloy with a given chemical composition. Here you can see the view of the used materials. It was a sponge titanium, aluminum granules, manganese in the form of chips, and in some experiments we use the alloy titanium plus manganese. Using these initial raw materials, by means of pressing through conical mold, we produce the consumable electrodes. And these electrodes were remelted into their ingots using MEM process, and ingots of the first remelt was remelted second time to get ingots with a diameter about 19 millimeters. The part of the ingot of the first remelting were hot rolled at this temperature and this deformation ratio to get a hot rolled bar. As you can see, the ingot of the MEM process is characterized by a good side surface without any surface defects, without oxidized area, and so on. The solidification structure of as-cast ingot is consists of equi-axis grains with average grain size about 1.5 till 2.5 millimeters. After the deformation, the macrostructure of the hot rolled bar was homogeneous across the entire cross section of the bar, and the average grain size is decreased greatly and was about 0.1 millimeters. In both cases, we not found pores, slack inclusions, or other defects. This table presents the chemical composition of the OT4 alloy for the ingot of the first remelting and for the ingot of the second remelting. The main conclusions are that the gas composition meets the requirement of the standard. This is very important for titanium alloys, and as you can see, the content of oxygen, hydrogen, and nitrogen does not exceed the allowed level. The second, that we found no difference in the element content between the bottom part and top part of the ingot. And the main result that there is no reduction in the content of aluminum and manganese in the alloy after double remelting. So double remelting using MEM process does not reduce the content of manganese, and level of the manganese in the ingot of the second remelting is equal to the content of manganese in the initial consumable electrodes. This slide shows the distribution of alloying elements across the radius of as-cast ingot and hot rolled bar. As you can see, the aluminum and manganese are distributed uniformly without any signs of zonal liquation. This slide presents the microstructure of the alloy for as-cast ingot and for hot rolled bar, the different regions of this ingot and bar. The alloy consists of alpha phase matrix with beta phase needle colonies. In general, the microstructure of the hot rolled bar is homogeneous and fine dispersed. And the main results that we not found pores, cracks, slack inclusions, and other defects in the produced hot rolled bar. This slide shows the micro hardness of different regions of the as-cast ingot and hot rolled bar. Besides the surface layer, the micro hardness of different regions, I mean the near surface region, mid radius, and center part of the ingot are uniform across the ingot or bar cross section. This table presents the results of tensile test. It was established that the mechanical properties of the hot rolled OT4 alloy bar produced by magnetically controlled electrostatic melting method meet the standard requirements for premium quality bars. And finally, the conclusions. The conducted research demonstrates the feasibility of producing titanium alloys with a specified manganese content and its uniform distribution using MEM methods. And second, the absence of alloying element evaporation in MEM process make it an effective technique for producing titanium alloys containing high vapor pressure elements such as manganese, chromium, boron, and other. Thank you for your attention. We are open to cooperation.
Thank you very much, Dr. Protokolov. And who has a question? Who would like to answer? Maybe I'll give you a question. Could I ask you, you have said, even in conclusion, that you haven't observed any changes in manganese, aluminum, and other elements that could evaporize, yes? Even after two treatments, or two remeltings. And could you say why? What is the basis of this effect? Why it doesn't changes in the metal melt?
The absence of evaporation of such element, we think this is due to two reasons. First reason is that we use overpressure of argon gas during melting process. This is not vacuum melting process. And the second reason is that the slag pool covers the liquid metal pool, and this do not allow to evaporate such components like manganese, chromium, aluminum, and others.
Thank you so much. And one more question I have. You told about the electromagnetic fields that occurs in a MEM process and current passage through the melt. And could you say what is the polarity on the electrode was, and could you change the polarity on the electrodes, and which one is better?
We use the AC electric current for the electrode, AC electric current, and we use the pulsed magnetic field, and we change the direction of magnetic field from the one pulses to other pulses to create the vibration. And this vibration allow us to refine the structure and steering the liquid metal pool.
Thank you so much. You have great interesting work. And who has a question now? Dear colleagues, does anybody want? No, thank you so much, Dr. Protokoyelov, for your very interesting, useful experiments and report. And could you continue with Konstantin Taranets? Are you here online, Konstantin Taranets? Konstantin Taranets, are you here? Okay. Igor Maximchuk. Igor Maximchuk, are you here? Dear colleagues, Igor Maximchuk? No? So let's go further. Sergei Nakonechny.
Dear Tatiana, dear Professor Tatiana Holub, can I suggest to make lunch and then we can continue after lunch if there are no any more the presentations for the speech right now?
Okay, if you have such a possibility, okay, we can use it. So, dear colleagues, dear auditory and online presenter, we are right now going to the lunch. I invite you to go to the lunch, and we will meet at 2 o'clock, and we'll continue our discussion and our very useful talk. Thank you very much that you are staying with us, and I hope to see you all again at 2 o'clock.
Dear colleagues, excuse us for some delays. We have some technical troubles, but currently I think we can start the session. We are now again with you. Are you hearing us? No? We can't hear you.
About now, can you hear
Yes,
me
currently
now?
it's okay. It's okay,
Thank
yes.
you so much. We are glad to see you again. It's great that everything is correct right now in you.
Yes, I see we can see each other and we can hear each other also. So I think we can
Okay.
start.
Super. So we can continue. Dear colleagues, dear auditory, nice to see you again, and we are ready to continue. I would like to ask, for any case, if the Dr. Sim here. No? If the invited speaker join us. No? So, okay, we can start, we can continue. The next one is Konstantin Taranets with the report Scenario for Structural Changes in Energy Consumption during the post-war recovery of metallurgical production in Ukraine. Dr. Taranets, are you here? We don't hear you. Unfortunately, we don't hear you. We can see you, but we don't hear
Hello?
you.
Hello?
Nice
Can,
to
can,
see you.
can you hear me?
Yeah, it's okay right now.
Hello, colleagues. Great
The floor is
to
yours.
be great to present my material and hope you see my presentation. Everything is okay? Could you please clarify if you see my screen?
Yes, we see it.
Yeah, okay, thank you. So the topic of our research, commonly with colleagues, myself, Konstantin Taranets, Olena Malerenko, and Alexander Tsvenko from Institute of General Energy of National Academy of Sciences, is related to the scenarios of structural change in energy consumption during post-war recovery of metallurgical production in Ukraine. The relevance of the topic is established by the number of factors, starting from the global context and necessity of decarbonization and reduce the dependencies from the energy and the resources from the core metallurgical productions, challenges of the industry itself, and needs to establish transition plans towards low carbon. Ukrainian dimension is that metallurgy is a basic sector of Ukrainian economy, responsible for 20% of exports, and needs to decarbonize according to the European Union plans and to be in line with those plans. The challenges of technological transformation, shifting paradigm from the basic blast furnace, basic oxygen furnace route toward electric arc furnace production, both using scrap and EAF and DRI routes of production, and the growing demand for electricity with reducing fossil fuel consumption and focusing on the consumption of low carbon electricity produced from renewables and nuclear energy sources. And scientific context, research into the mechanism for adopting Ukrainian economic and regulatory aspects. The object of the study to assess energy consumption is the basic metallurgical core production systems, stopped with liquid steel. So we analyze the energy consumption pathways, starting from the raw materials production to the primary production, sintering, coke production, blast furnace, casting, and producing the steel in different routes. And the subject of the study is energy and particular electricity demand for the different scenarios of such complex transformation in Ukraine. So methodologically, at the moment, we are using quite simple approach, just analyzing the energy and GG emission consumption based on the specific emission and energy performance indicators related to each route of produced steel, also using the scrap ratio and the scenarios of the total steel production in Ukraine in ton of liquid steel, and also some alignment on the technological routes of development, the further technological pathways. So we developed the two scenarios for post-war recovery of the sector. First is related to the keeping the total production volume at 10 million ton of steel per year by 2035. The volume of production after losing of assets from in Mariupol down from 20 plus million tons per year to 7.4 million in 2024. And the second scenario is related to the gradual increase of production capacity and reaching pre-war rate of 20 plus million ton of steel per year by 2050. As per the particular technology used to produce steel and to satisfy those demand, we aligned with projections made by the group of authors from Nekrasov Institute of Metallurgy, the pathways of further substitutions, basic furnace, basic oxygen furnace route with electric producing route, coupling both DRI and electric arc furnace using scrap, with some correction on the short-term interval, because on Zaporizhzhstal we still have open hearth furnace, Martin furnace, so we assume that it still be in operation within short-term interval, and then for sure it will be substituted with other technological pathways present. So what we achieved, first of all, we analyzed the overall GG emission trends in the sector in both scenarios, and found that in both scenarios, 10 million ton steel per year and 20 million ton steel per year, the overall GG emission factors for the time horizon 2030, from 2030 to 2040, will be below the country target, the sectoral targets established at the country level, and we have the targets of achieving net zero by 2050 and achieving nationally determined contribution minus 65% of GG emission reductions from 1990 year. So for the sector itself, there is a time horizon 2030 when in the provided technological pathway, the GG emissions will be in line with those sectors. The challenge will be after 2040, when the sector will need to achieve net zero, but it's not feasible, it's not possible to establish in such short-term horizon such type of hydrogen produced to support the core production facilities. As per the shifts energy consumption in both scenarios, 10 million per year, we analyzed the shifts in overall consumption of coking coal, energy coal, natural gas, and electricity, and also adding to our analysis some pragmatic consideration regarding biomass use in the sector. We found that the relevant cases already exist in Europe and across the world. You see here that in the first scenario there will be optimization in the overall energy consumption and substitution of both coke and natural gas, mainly also energy coal with electricity on the left side, with a scenario of 10 million ton of steel per year, and the increase of the overall energy consumptions, mainly with increase of electricity demand needed for sector when this steel demand increased to 20 million ton of steel per year. This increase in energy demand is the rationale for that is the share of natural gas used for DRI. Target DRI technology will be moderately substituted in 2030s by hydrogen, and then fully substituted by hydrogen by 2050. And the processes of hydrogen electrolysis require a lot of electrical capacity. Based on our current assumptions, from 2 to 4.4 additional gigawatts of electrical capacity will be needed in Ukrainian energy system, especially for metallurgical sector development pathways mentioned. So what are the current outcomes? So we developed two scenarios, 10 and 20 million tons of steel per year. We analyzed the trends of total energy consumptions in its transformation by 2050, substitution of electricity, of coke and natural gas with clean electricity. We included the technological transition scenarios aligned with sectoral understanding and how the technological pathways will be changed in time. And we preliminarily estimate how much additional electricity capacity will be needed to support such transition. Our further goal is to, let's say, increase the number of variables used for such model and define different pathways using difficult policy measures, demand measures for steel, steel quality matters, and the structure of the financial final product that we will produce in Ukraine. So the synergy between pure metallurgical complex and its further technological transformation and energy complex to support metallurgical sector with available capacities, non-fossil fuel electricity in the particular years is a core to achieve the policy related targets to decarbonize Ukrainian economy. Thank you so much.
Thank you very much. Your report is very actual. And dear colleagues, who would like to answer the question? Does somebody would like to answer? So I'll answer maybe. Okay.
Yep.
I'm into you. I'm sorry. There is a question, and then I will ask you.
Dear Konstantin, hello. I have a question to you. So, in which areas of the metallurgical industry is it advisable to introduce artificial intelligence to accelerate the post-war development of the industry?
Thank you so much for this question. As per my understanding and per my knowledge of metallurgical sector in Ukraine, the core area for using artificial intelligence is rolling departments, because technological experts of all companies in Ukraine more focused on the quality of the finished products, flat products, tubes, slabs, and others. So a lot of deviations and a lot of area to increase the quality and reduce the non-liquid production is demanding AI for using. But also the area I described also will require some artificial intelligence, because forecasting the energy needs and the transitions of the energy emissions consumption and forecasting the metallurgical steel production site of its demand in different energy sources is also another promising area to use artificial intelligence capacities.
Okay, I'll go your point.
Thank you so much.
Thank you.
Any
Thank
question?
you.
Okay, I mean. thank you very much for a very interesting report. And based on your knowledge and understanding of this subject, can you advise the possible ways for the Ukrainian companies to increase the competitiveness on the foreign markets for the metallurgical companies in particular?
Thank you so much for this report. I guess this shift toward green steel production itself is a lever to increase the competitiveness of the sector itself, because we are trying to integrate into European steel market. And European colleagues also postponed the non-quotas supplying for another 3 years. In European steel industry already established its decarbonization targets, and most of all European companies already investing into the green steel producing technologies. So at least some minimum efforts. I understand that we have the war events and it's not feasible for the companies to establish such type of targets to shift fully into the electric metallurgy and establish DRI. But anyway, the movements towards the producing of the green steel will support our industry to integrate into the European Union supply chains.
Thank you very much. And I have a question. You talked about the energy consumption, and could you give the recommendation? What is the best source of energy will be better after the reconstruction period in Ukraine?
It's quite a good question. At the moment, according to the last events and lack of capacities in the Ukrainian energy system and our reliance on the import from NSOE electricity, each megawatt matters. So at the moment, we are demanding for any available additional megawatt in our energy system. But for sure, to support the energy clean transition, we will need mostly long-term reliable non-fossil fuel electricity generation. First of all is the nuclear generation, because it's the only energy sources at the moment that could produce, that could support the steel sector with the baseload demand fulfillment, but also different configuration of renewables, solar, hydro, wind, but backed with storage or any other initiatives to say feed demand and supply, because most of the classical renewables, its production related to the stochastic variables depending on the weather condition, but metallurgical sectors will need this strong and solid baseline loan for 24 hours per day. So first priority is nuclear, second priority is renewables with storage. That's our position.
Thank you very much. Dear colleagues, do you have more questions? No, thank you very much for your vivid and very interesting report, very useful in our time. And the next one is HighMatTech-2025, the physical nature or the high damping capacity of magnesium alloys. Dr. Maximchuk? Dr. Maximchuk, are you here?
Yes, I'm present.
Yeah, we hear you. So the floor is yours. You can start.
Yes, okay.
Yes, we can see your presentation.
Sorry, just a moment. You see my screen?
Yeah, we can see your presentation. You can try to change the slides. Please.
Sorry.
Dear Igor Maximchuk, we can see your presentation, but not in full view. Please try again, but try to share your screen, not window, but screen. And then please
Yeah,
use
okay.
F5, because we don't see full screen, full view of your presentation.
Yes, I made it, but I don't have result.
You should stop presenting this presentation and then try again to share screen, not window, but yes, and try again. But screen, you can choose screen. Hmm? Screen.
Sorry.
And F5.
Sorry. I don't make the full screen presentation.
F5. Not?
Not what? Oh, yes.
Yes, it's okay, excellent.
Thank you, sorry, ma'am. Dear colleague, my report indicate to physical nature of high damping capacity magnesium alloy. It was known that magnesium has a higher damping capacity among other metals. Therefore, it alloy readily used in devices requiring vibration damping, especially the alloy, magnesium alloy based on aluminum magnesium systems. Damping capacity in materials ability to absorb despite mechanical energy, particularly from cyclic stress vibration, by converting it to the heat through the internal friction. Damping depends on many factors: purity, again size, alloy composition, thermomechanical treatment of magnesium materials, their microstructure, and substrate temperature, frequency, and stray amplitude. Understanding the physical nature of damping is important to development of design new highly damping magnesium alloy. Despite numerous studies, several aspects remain unclear, including the influence of or effect of temperature and alloy composition on damping ability. The literature review and our research results are summarized in the diagram below. A small strain amplitude, elastic energy dissipation, is caused by oscillation of dislocations in segments and is described by the Granata-Lucia model. It's the first interval. The next interval combines dislocation slip and the onset of the twinning between mechanisms. The third interval is variable interval is associated exclusively with twinning process. On this slide, we have the figured in presented the data of internal friction as function of the strain amplitude under different treatment of polycrystalline magnesium. This data was presented in the Journal of Mathematical Physics and Mechanics and received by using the method of ultrasonic investigation. We reported this data on the in the Granata-Lucia coordinate and we obtained the interval of amplitudes where dislocation damping is according to the Granata-Luque model. On the even the small addition of alloy, even the magnesium technical purity shift the dependence of internal friction on strain amplitude toward to the higher strain amplitude, as we can see in figure 2. In figure 2, sorry. This might be a connection with data presented Barnetton the journal Metallurgical and Material Transaction, wherein summarize the data many investigations about the critical resolved shear stress, the action in magnesium. It was very known that in magnesium there are not enough independent dislocation slip systems to realize uniform deformation due to large difference in resolved critical stress between the slip systems. Therefore, twinning is one of important and necessary mechanisms for satisfying this criterion. As we can see from the plot, from this graph, the critical resolver shear stress is more higher than for basal slip. In prismatic slip is more higher than the activation of basal slips. The system of sliding system in magnesium present in the right graph. We investigate the damping capacity magnesium using loading unloading cycles in tensile stress. The exodometer was placed directly on the working part of the sample to accurately measure the elongation in the experiments. On the fig 2, typical stress curves for the magnesium alloy system and the cycle only is presented. We define the conventional limit of twinning, sigma 0.002, as a magnitude of stress and at which the twins start to grow. The start of twinning is accompanied by acoustic emission. We calculate, as we can see from the figure 1, damping capacity as ratio of loop area to area under the load curve. In the right figures, we presented in light size of one of the loop. We can see the we can see from the right figure the loop line is not smooth curve, as many research imaging in your publication. The curve is stepwise in nature, with isoelastic deformation alternating with twinning. This allows us to more accurately determine Young modulus and determine the conditional limit of twinning. On this slide, present the strain stress curves for magnesium alloys under certain loading at room temperature. As can be seen from the figure, the increase, the solubility of magnesium, the solubility of aluminum in magnesium at room temperature is approximately 4 to 8%. At higher concentration, the magnesium 70 and the aluminum 12 transforms in a magnesium market. As the concentration increases, the volume fraction of this fast increases. Thus, it is necessary to take into account the different structural states of the materials when analyzing the nature of damping. And can we see from figure 6, with increasing aluminum concentration, the conventional twinning limit is significantly higher than the for pure magnesium, with exception of the alloy containing 3% of magnesium. The peak in the low elastic strains may be explained by dislocation-induced damping mechanism. However, its nature is not fully understood and requires further research. We on this plot presented the damping dependencies on aluminum concentration and temperature. Once the aluminum concentration increases, the damping peak shifts toward to higher stresses. When stress reaches value corresponding to activation of non-basal slip, the contribution of twinning decreases significantly. This explains the presence of peaks in the damping curves. With increasing temperature, attenuation decreases most significantly for pure magnesium and remains virtually unchanged for the alloys. The relationship between the damping characteristic and the realization of various mechanisms depending on stress, magnitude, or vibration amplitude for magnesium and magnesium-aluminum alloy is established. The main differences is summarize my speech. I can make the important conclusion. The main differences in nature damping mechanism. When the dislocation mechanism is implemented, even microlaying reduces the damping of pure magnesium. Conversely, with the twinning mechanism, damping can be higher within the solubility limit of alloying elements. The presence of phase precipitate reduced damping below the value inherent in pure magnesium. This conclusion is important when design magnesium alloy with higher damping properties. Thank you for your attention.
Thank you very much. Dear colleagues, who has questions? Please raise your hand. Dear colleagues, so I'll ask, could you tell us if the same materials but made with different methods, traditional powder metallurgy, additive technology, and so on, will they have the same vibrational absorption mechanism?
Sorry, the sound is very bad. I don't understand you.
Okay, I'll try to explain another way. If you have the same material but made by different methods, traditional, powder metallurgy, additive technology, do they have the same absorption mechanism? The same material but produced different technology. Do they have the same absorption mechanism?
The absorption mechanism we investigate in cast magnesium alloy, and it depends of strain amplitudes in various strain amplitude action, various damping mechanism. In the low strain amplitude, there prevails the dislocation mechanism. At the high amplitude, the detwinning mechanism.
Okay, thank you. And who would like to answer the question? Me again. Okay, so I'll ask one more question. How do the size and the shape of magnesium phase influence on the damping properties?
Sorry.
How do the shape of magnesium grain influence on damping properties? Shape of magnesium grain influence on on damping properties.
Sorry, very bad sound. I don't understand the questions. Excuse me.
Is the shape of magnesium grains influence on damping properties? The shape, is it influence of magnesium grain?
Sorry. Bad sound.
I'm sorry. So thank you very much for your speech. Very useful and interesting. And we move further. And the next one is Sergey Nakonechny. Aluminium, chromium, titanium, ferrum 0.5, niobium 0.5, high entropy alloys prepared for mechanical alloy. Sergey Nakonechny, are you here?
Не слышу. Я вообще, когда она говорит, я вообще не понимаю. У нее как-то сливается все. Я не понимаю. Ты как-то, хоть как-то я что-то укладывалась.
Dr. Maximchuk, thank you very much for your presentation. And we are asking about Sergey Nakonechny. Are you here? Sergey Nakonechny.
Good day.
Yes, we hear you. You can start your presentation. The floor is yours.
Hello.
Hello, nice to see you.
You hear me? Yes.
Yes, we are. We do it.
So, yes. Word for presentation. Yeah.
Yes, it's great. We can see your presentation.
Yes. Today I'm present for you research in field of high entropy materials. In current research, we develop we know that metal matrix composites are one of most common and best in direction of application properties, mechanical, corrosion, oxidation, wear resistance. That's why it is very high potential for different application. However, the limitation, one of limitation of this type of materials is matrix. For usual common metal materials as simple metals and their alloys, each have limitation of strength, hardness, and other properties. That's why we try to develop new materials based on high entropy alloys. However, these also have some problems opportunity. First is the composition of matrix. We know that there are different structures and can be different refractory compounds that use as reinforced fuzz. However, in our works, we try to develop the materials composite which forms in during sitting. So we develop metal matrix, which is high entropy alloys, and introduce to it non-metals elements such as carbon, boron, and other. If we research for different non-metals elements, the very high potential have boron introduction addition. However, there are not very much research in this field, and mostly for high entropy alloys, composite is based on refractory metals. So we develop more lightweight high entropy alloys based on aluminum, iron, chromium, titanium, and niobium. For less weight of alloy, we introduce less content of iron and niobium. So firstly, we choose mechanical alloying production method for to prepare our high entropy alloys. We see that in case of other alloys which we research, the alloying of materials occurs between 5 or 10 hours. While in this case of this composition, we have interaction after 1 hour of mechanical alloying. And after 20 hours of mechanical alloying, we have homogeneous high entropy alloys based on 2 solid solution, which, according to research of microstructure of particles, is based on 2 more hard and strange materials as chromium and niobium. While at first hours of mechanical alloying, the interaction of aluminum and titanium firstly occur. After 20 hours of mechanical alloying, we have homogeneous, practically homogeneous alloy from 2 solid solution, which is based on chromium and niobium, and also some impurities of tungsten carbide from grinding bodies. And also we research lattice parameter and other properties such as hardness of our alloy. That's why we know that after 20 hours of mechanical alloying, we have prepared final alloy with its complete structure. And we also provide sintering with boron addition of this alloy. We obtain different structures adding from 0.5 to 1.5 mole of boron, and obtain different reinforcing phases. In case of free boron high entropy alloy, we obtain metal matrix composite structure with two solid solution and also obtain very high amount of aluminum oxide, which was obtained by electron beam sitting. So it's we have very short time of sintering, heating, cooling. That's why interaction of aluminum with oxide, which was not reduced due to short time of sintering. But when we adding boron, we have less of aluminum oxide, black phase, and start to obtain different boron containing phase. In case of low content of boron, we have very complex boride based on titanium and niobium. While in case of increase of boron content to 1 mole, we have based on XRD research titanium boride phase, not diboride but boride, which is was confirmed by more rectangular shape of phases growth. It also based on other research from different composition, which we have also. When we add more of boron, more than 1 mole, we have the interaction of solid solution with boron, which lead to formation of more strange boron doped matrix. We also research mechanical properties not presented in this presentation due to lack of time. The hardness of most of boron doped composites is practically the same, in difference of 1 gigapascal, from 12 to 13 gigapascal, while fracture toughness are more high in alloys doped with 1 mole boron and 0.5 boron. That's all. Thank you for your attention.
Thank you very much. Dear colleagues, who has a question? Who would like to answer?
Yes.
Please raise your hand and I will come to you. Okay.
I have some questions. How do the condition of phase manufacture from powders, temperature, pressure affects the structure and phase state of alloys?
Please, can you repeat? Not hear very well.
The sound is not very good. We can't hear you very well. So maybe you can write the questions into the chat.
Yes.
1, 2, 3. Let's try to check our voice because we need it. 1, 2, 3. Because we will have a report. 1, 2, 3. Can you hear us?
Yes, currently it's much more better.
Okay, so repeat the question, please.
Yes, ready.
How do the condition of phase manufacturing from powders, temperature, pressure affects the structural and phase state of alloys?
You mean mechanical alloying?
Yes.
Pressure and temperature.
Yeah, how do they affect in a further manufacturing?
Currently, we research only one of alloy. We not very treat different condition. We know that more or high temperature parameter rotation speed of planetary ball mill. That pressure was not controlled. This was just mixture of powders in grinding bodies in presence of some petrol to avoid excessive welding. While to avoid very high temperatures, we use low rotation speed of 400 of rotate per minute. This was first control. It's only starting research, more fundamental. Currently, we not control more of different parameters.
Thank you very much. And I have one more question. You told that you have checked the lattice parameters of your composition. What kind of lattice parameters have you studied?
It was firstly solid solution. When we introduce first boron, it has not boron. Largest parameters. We research how much it changes during mechanical lowering. So we control when the formation of main crystal structure will be ready. So elemental composition will be more format homogeneous.
Thank you very much. Thank you for the interesting report.
Dear Tetiana, we have one more questions here.
Okay,
Hanna
yes.
Borodyanska.
Thank you.
I have one question about slide 6. Yes. Before. Okay. So interesting microstructure you are received by your entropy alloys, I think, and I saw very interesting dependence of boron the content, and so different. It's mean only boron content can change your phases, second phases.
In
So
this case, yes, we have research also other some composition prepared by the same way of mechanical alloying. They have more different structure. They have more changes in shape and size of bright inclusions and their stoichiometry.
Yeah.
For example, in other alloy we have only titanium boride inclusion, which with increase of boron content lead to titanium diboride, but not such different composition. It's a case of these alloys.
I see.
That's why it's
But
research.
what phases is black on each microstructure? I saw black. It's
some aluminum oxide. This is we use electron beam sitting. In our case, we want only see watch secondary phases, watch borides is forming, because we see with different composition, not always form the boride which we predict. That's why we use height short.
I see. Thank you.
In future, it will be more optimization of sintering method to avoid also more. So reduce oxide in initial component during sintering and other.
Okay, thank you.
Thank you very much. Dear colleagues, does somebody have any question? No? Thank you very much. Thank you for such a great report. And the next one is Anna Kononenko, analysis of fatigue crack growth rates in railway wheel metal made of steel of different chemical composition. Dr. Anna, are you here?
Yes, hello, good afternoon, dear colleagues.
The floor is yours.
Thank you for the opportunity to present to you today the research result that we obtained that our team obtained in the project which was carried out within the framework of bilateral international scientific cooperation with the Federal Republic of Germany, founded by the Ministry of Education and Science of Ukraine. The problem of fatigue failure is so one of the most urgent in ensuring the durability of railway wheels. The accumulation of damage due to fatigue, plastic deformation, and wear significantly reduce the service life of railway rolling stock. Destruction under the influence of cyclic loads is especially dangerous because it occurs suddenly at their level, which is most lower than the yield point. So the study of fatigue fracture resistance indicators require special attention. In industrial steels, there is a micro inhomogeneity of the chemical composition, especially the carbon content, which can affect the process of fatigue crack growth and reduce the service life of the product. The most common indicator determined as a result of fatigue test is the endurance limit. However, this parameter is of a generalized nature and does not allow identifying individual stages of the development of the fracture process, which, as it known, included several stages: the nucleation of the fatigue crack, its stable growth, and final failure. Each of the specified stage is characterized by a specific fracture mechanism as well as the characteristic effects of various factors. Taken into account the possible chemical heterogeneity, it is important to understand to what extent changes in the chemical composition can cause changes in the values of the resistance indicators of the metal to fatigue cracks growth. In this regard, this study is aimed at establishing a relationship between the chemical composition of steel for railway wheels of the year 7 and year 8 grades, focused on variation in carbon content and fatigue fracture parameters such as crack growth rate, threshold value of the stress intensity factor, fatigue life, and critical defect size. This study was performed on fragments of railway wheel rims made of year 7 and year 8 steels. The carbon content fluctuation was 0.02%. Other elements met the requirements of the standard. The tests were performed on compact samples 30 mm 6 according to ASTM E399 and cyclic loading. Crack growth control was checked by optical method and by the method of compliance change using a special strain gauge mounted on the sample. The crack was introduced perpendicular for the rolling surface, simulating the typical development of an internal crack in the railway wheel rim. The service mechanical properties were also determined during static tensile and 3-point dynamic yield test using standard method. Studies of the mechanical properties of the rim metal of the wheels ER7 and ER8, which are standard in accordance with the requirement of regularity documentation, have shown that a fluctuation of the carbon content by 0.02% within the great lots to an increase in strange characteristic by up to 7 and an equivalent decrease in plasticity indicators. The most significant change in the chemical composition affected the impact tonus value. This indicator decreased by 13.22%. The microstructure is ferrite and perlite with an increase in the carbon content. In the steel, the grain size increases slightly and the almost of ferrite decreases. We built a fragment of kinetic diagram showing how to crack growth rate changes with cyclic loading. The main parameters of fatigue crack development are K V star, the stress intensity at a small crack growth rate, and the slope showing how fast the crack grows, and KFC, the critical value when the sample breaks. In this steady growth region, the slope and change only slightly about 10%. Detailed values of all coefficients are presented on the next slide. Another indicator of the sensitivity of steel to stress concentrators can be fatigue life, which is defined as the number of Lorentz cycles before failure. It was found that when the carbon content in wheel steels increases, the steel becomes less resistant to fatigue. Even small variation of carbon, about 0.02%, can shorten the lifetime of the material. For example, in ER7 steel, the number of loading cycles before failure decreases by about 10%, and in ER8 steel by about 20%. The critical crack length, the size of a crack that causes failure, was calculated using a well-known model for semi-elliptical cracks and experimental data on fracture tonus, KFC. Considering that in real service condition, the maximum stress in well rim can reach 400 megapascal, it was shown that a higher carbon content reduces the size of crack that can safely exist. Even a small variation of 0.02% carbon decreases this critical crack size by about 8% for ER7 steel and by about 18% for ER8 steel. As a result of an analysis of the research result, it was found that an increase in the carbon content in the studied steels for railway wheels leads to an increase in stretch indicators, but at the same time, the values of the plasticity and impact toughness indicators, the critical fatigue crack length and fatigue crack growth indicators decrease. It was found that fluctuation of the carbon content in wheel steel within the limits of possible chemical microkinetic micro heterogeneity lead to a slight effect on the rate of steady growth of fatigue crack up to 10% and the stage of its steady growth. The second linear section of the kinetic diagram of fatigue fracture for steel grades year 7 and year 8. It was found that increase in the carbon content in wheel steel leads to a decrease in the number of cycles to failure by 10% for year 7 steel and by 20% for year 8 steel, and a decrease in the critical size of the fatigue crack by 8% for year 7 steel and by 18% for year 8 steel. My report is complete. That's all I have. Thank you for your attention.
Thank you very much, dear Dr. Anna. Dear colleagues, who has question? Raise your hand and I'm coming to you. Dear colleagues, yes, I'm coming.
Dear Dr. Hanna, my question is what practical recommendation for railway wheel production can be made based on the results of changing the carbon content in the chemical composition of investigated steel? Thanks.
Thank you. It's a good question. As for the production of wheels, the recommendation may be to strive to increase the uniformity of the distribution of chemical elements and structural state. This can be regulated at various stages from the manufacture of steel billet to heat treatment of the wheels. For consumer of this product, for railways, a recommendation may be given on changing the frequency of wheel inspection for ensure reliable operation.
Thank you very much. Who has more question? Okay, Simon.
Why does increasing the carbon content of wheels still reduce fatigue life but have little effect on crack growth rate in the linear section of the KFFD?
Thank you. Particular life describes the behavior of metal during the rapid crack growth at the final stage of failure. At this point, stress becomes highly localized and the structural state and phase properties can significantly influence of the crack growth. This issue requires further investigation to better understanding how the microstructure affects the mechanism of fatigue crack growth.
Thank you very much. Dear colleagues, who has question more? Okay, I'll ask dear Dr. Anna. As I know, wheel work in pairs with rails, yes? And did you investigate this moment? How do they work in pairs and rails condition effect on fatigue cracks growth? You know, in Ukraine, the condition of railways not so good. So why I ask, do the condition of rails affect on fatigue crack growth in wheels? How do you think?
The wheels should be less durability than rails. In this case, exploitation will be safely.
Thank you very much. Thank you for your vivid report. Very interesting and useful. And we are continuing. The next one is Igor Chuiko on the formation of martensite in low carbon alloy steels for welding applications during slow continuous cooling. Please, Dr. Chuiko, the floor is yours.
Greetings, dear colleagues. Can you hear me?
Let's wait a little bit for the presentation. We are switching and sharing it.
Okay, my name is Igor Chuiko, and today I would like to present for your attention a short report on the results of our research entitled On the Formation of Martensite in Low Carbon Alloy Steel Wire Rod for Welding Application during Slow Continuous Cooling. So, the presence of hard structures of cohesion in steels intended for welding application is most often discussed in scientific literature in the context of their formation in the weld metal and the heat-affected zone of the welded component. However, information about the formation of such structures in steel welding materials during their manufacturing processes is quite limited, and certain aspects of microstructural evolution and the characteristics of the resultant phases remain insufficiently studied. Solid wire for welding is most commonly produced from low-carbon steels with various alloy systems. This type of wire is traditionally manufactured by cold plastic deformation through drawing of a wire rod with a diameter from 5.5 to 6.5 millimeters. One of the key challenges currently faced by manufacturers of steel wire for welding application worldwide is achieving maximum plasticity in the metal before delivery to hardware plants. This need arises due to the ongoing technological advancement in the field of hardware production and the integration of modern equipment capable of producing wire at high drawing speeds with significant degrees of unit deformation. Such processes demand high-quality raw materials, in particular a wire rod. Rational microstructural design is a key principle in producing highly plastic wire rod for the efficient manufacturing of welding wire from low-carbon alloy steels. The presence of hard components such as martensite, bainite, or their mixtures in the wire rod structure is undesirable as they increase the risk of metal failure during intensive cold deformation by drawing. Minimizing these hard phases remains an urgent scientific and practical challenge. So, the aim of this study is to determine the mechanism of martensite grains formation during slow continuous cooling of low carbon alloy steel wire rod for welding application from austenitizing temperature down to room temperature. Next slide, please. No. Okay, this one. The material used in this study was steel, chromium, molybdenum, vanadium 1 silicon with the chemical composition present in table 1. The samples were subjected to thermal cycles using an automated label thermal deformation simulation system. The thermal cycle involved heating the samples to the temperature required for complete austenitization, holding them at this temperature, and then continuously cooling at 3 controlled rates to room temperature, as illustrated in figure 1. Metallographic analysis was conducted using an optical microscope and a scanning electron microscope. The hardness of individual structural components was measured using a micro-hardness tester. The chemical composition of the individual phases was determined by energy dispersive X-ray spectroscopy and Auger electron spectroscopy. Next slide, please. The microstructure of the samples after the experimental head treatment modes is shown in figure 2. In all cases, the steel structure consisted of a ferritic matrix with isolated areas of perlite and bainite. Additionally, relatively uniformly distributed individual martensite grains were observed in the plane of the polished section, exhibiting high hardness. Some of them are marked with circles in figure 2. Scanning electron microscopy confirmed the needle-like morphology of the observed martensite as illustrated in figure 3. The volume fraction of structural components after the experimental head treatment modes determined based on microstructural studies and their microhardness are presented in tables 2 and 3 respectively. Particular attention is drawn to the fact that the volume fraction of martensite grains in the steel structure and their size increase as the cooling rate decreases. At the same time, the amount of perlite and bainite decreases accordingly, while the amount of ferrite increases. The fact of such microstructural evolution was of both scientific and practical interest. Next slide, please. The formation of shear transformation products from austenite during slow continuous cooling of the steel can be explained in terms of the dynamic change in the chemical composition of individual phases during temperature reduction, primarily due to the diffusional partitioning of carbon and other alloying elements between the alpha and gamma phases. To confirm this hypothesis, the chemical composition of individual structural components in the investigated steel was determined after cooling at the minimum rate. The results of this study are presented in table 4. It was found that during slow cooling of investigated steel from austenitization temperature to room temperature, active partitioning of alloying elements occurs between structural components. Carbon and manganese are actively expelled from the forming alpha phase into the remaining gamma phase during cooling, leading to an increased concentration of these elements in the newly formed austenite transformation products. The lower temperature at which a structural component forms, the higher concentration of these elements in it. Silicon, as a ferrite-forming element, actively enriches the alpha phase and is present in martensite at a minimal concentration, as by the time martensite forms, the diffusional partitioning of this element appears to be largely complete. Based on the obtained research results and available literature information, it is possible to propose the following mechanism for the formation of high carbon martensite grains in wire rod made from low carbon alloy steels during slow continuous cooling from the austenitic region down to room temperature. As illustrated in figure 4, after full austenitization, the alloying elements in the steel are distributed relatively uniformly throughout the volume. During cooling below the critical temperature AR3, the growth of ferrite nuclei provokes the displacement of carbon atoms into the untransformed austenite by the moving fast boundary due to the different solubilities of carbon in the alpha and gamma phases of iron. During the development of the diffusional transformation in low carbon steels, when the amount of ferrite significantly exceeds the amount of remaining untransformed austenite, the carbon concentration in austenite can exceed 1 weight person. This process leads to the thermodynamic stabilization of the gamma phase. The diffusional enrichment of the retained austenite with manganese also has an additional stabilizing effect. Depending on the actual local carbon concentration and the cooling rate, this austenite may undergo perlitic, binitic, or martensitic transformation as the temperature decreases, which is observed in the studied steel. Thus, the diffusional partitioning of carbon and manganese between the alpha and gamma phases is responsible for the thermodynamic stabilization of austenite in the studied steel down to low temperatures, close to room temperature. Nevertheless, the driving force of the transformation increases with undercooling, which ultimately leads to the diffusionless formation of martensite, which inherits the high carbon and manganese content from the transforming gamma phase as illustrated in figure 4. The results of conducted research are important for developing scientifically based thermomechanical processing modes for wire rod made from low carbon alloy steels, including those intended for welding application. The most critical factor affecting the stability of subsequent cold deformation of wire rod is the presence of martensite in the metal structure, as mechanical stresses are localized around it during drawing, leading to formation of microcracks in the ferrite matrix, which may potentially result in the development of a main crack and wire failure. On the one hand, the cooling of wire rod after hot rolling must be sufficiently slow to allow formation of a large amount of soft ferritic components in the steel structure. On the other hand, it must be fast enough to prevent significant diffusional enrichment of the residual austenite with alloying elements, primarily carbon and manganese, and the subsequent transformation of metastable high carbon austenite reagents into hard martensite. Determine the optimal temperature time parameters for low carbon alloy steels wire rod cooling at the final stage of thermomechanical processing will be the subject of future scientific investigation by the authors of this study. Thanks for your attention, and special thanks to the organizers for the opportunity to speak at this interesting conference. If you have any questions, I'm ready to answer them.
Thank you very much, Dr. Chico. Dear colleagues, who has any question? Okay, I'm coming to you.
Thank you for your presentation. I have one question. What's the result selecting investigated steel in this work?
Thanks for your question. One of the main material used for welding heat-resistant low alloy chromium molybdenum and chromium molybdenum vanadium steels of the perlitic class is welding wire made of investigated steel grade. So the use of such wire in the manufacturing and repair of power, chemical, and petrochemical equipment is becoming increasingly relevant in the context of renovating damaged infrastructure facilities and transportation infrastructure of Ukraine.
Thank you very much. More questions, dear colleagues? Okay, I'll ask you. Could you highlight what is the scientific novelty of your findings? How do your results of the study fundamentally differ from available in literature?
It's a very interesting question, and I will try to answer it briefly. The analysis of the literature has shown that the formation of high carbon martensite in wire rod made of low carbon alloy steels had not been previously confirmed. So it was earlier assumed that the main reason of martensite formation in such steels is the segregation of alloy elements stabilizing austenite, primarily such as manganese. However, the diffusional partitioning of carbon during the formation of structural constituents has not been confirmed, and in our study, this has been demonstrated for the first time.
Thank you very much. Dear colleague, does anybody have questions? Thank you very much, Dr. Chico, for the very interesting report. And the next one is Victor Horban, High Entropy Materials. Victor Horban, are you hear us? Are you here? Victor Horban, are you online? Yes, we can see. But cannot hear you still. We see your presentation, but cannot hear you. Are you hear us? Dr. Horban.
Colleague, here is a presentation of high entropy materials, a new class materials. This class of materials has increased properties of basic characteristics in the wide range of temperature in comparison in other materials. This class of materials has increased properties of the alloys. There is no basic element, and therefore condition of create for self-organization leading to minimum energy cost. For example, 26 element, 1 further layers. 1 further layers. Is entropy of system which given thermal stability and reduced diffusion. This leads to the fact that here can operate it up to 0.6 melting point, in which clearly in this slide. Effect distortion and enthalpy of mixing on fast formation is heat entropy alloys. This thin phase solid solution, multi-phase, amorphous phase in other regions. There is each of more than 1,000 samples of cast and coating here using microindentation, X-rays, structure analysis, and electron microscopy, always used to indefinite in characteristic of here. They included electron concentration determined on phase state of high entropy alloys. Each phase is formed in our region of electron concentration. Sample change of electron concentration leads different phases. Alloys containing only one element. thin fast phase formed when electron concentration limit 6 and 6, 7 and 3 electron percent, and distortion is greater than 12%, and enthalpy of mixing of power was greater than minimum 30 kilojoule on mole, and the total enthalpy of mixing is negative. Sigma phase from each element of here must form sigma phase in two component system with any other element of the alloys. Enthalpy of mixing, the force of interaction between different atoms. It has been established that the decrease in the mixing enthalpy towards negative values in high entropy alloys reduce of lattice parameter. At the same time, it leads to the increase the elastic modules. For all types of solid solution high entropy alloys. The distortion of the lattice is reduced result of the presence of atom with a different radius. Distortion in here by prevention to movement of the dislocation and contributed to stress. As shown in this slide, the distortion proportional elastic deformation. The relationship between the ratio. They have also determined the role of most refractory element in the form on the lattice parameter of here. The relation between ratio deviation of the experimental determination elastic module from calculation and the ratio deviation of the lattice parameter calculated here from lattice parameter of most refractory element is these alloys have a proportional dependence. This makes it possible performance elastic module calculation for solid solution here. This formula. A similar dependence is observed in high entropy carbide. In this slide, show the modules calculation and modules experimental, very good. A similar dependence is observed on form energy carbide. Effect lattice parameter on elastic modules. The lattice parameter determines the elastic module in cast solid solution and coatings based on them. On intermetallics, nitride, and carbide. Effect lattice parameter on plasticity silk fast phase. For here, based on the BBC lattices, the larger of lattice size, the more ductility of alloys. For here, based FCC lattice, the larger of parameter size, the less ductility alloys. On the basis of obtained data of hardness, elastic modules, calculated values of average atomic radius, elastic modules, distortion, mixing enthalpy, a program for calculation hardness of solid solution here is proposed. In this slide, high ash calculated, ash experimental, the IPMS, and Cook loves it. Take it a basics, where elastic module is calculated accounted the proposed formula slighted density with correction for the influence and mixing enthalpy. The elastic deformation is replaced by distortion. The elastic stress is replaced by hardness. No, the hardness value is possible of determined from hardness was carried out using the formula yield stress equals 0.3 hardness. This slide shows the values of yield stress take from article for yield stress calculated from that alloys compound in atomic percent. The present date shows the calculation T stress is quite close to the article that of the various authors. As can be seen, most of here studies carried in China. In the possible of carry out preliminary calculation, melting temperature, coefficient of thermal expansion, and function. Possible calculations for properties of carbides. This is opens the possibility preliminary selection composition of zinc fuzz here with regard of strength at room and working temperature, taking in the account the specific gravity and ductility. The slide present comparison that of dependence experimental and calculation yield stress on ratio of test temperature to the melting temperature. This slide shows hardness limited obtained on refractory component on here with IPMS and Kharkov Institute Physics and Technology. In sample, the comparative physical and mechanical characteristic of diamond and high entropy nitride quality obtained by microindentation. For the technology play a big role on obtain these results. This slide shows the results here quality produced by magnetron method and vacuum art method Bulat 6. The advantage of the vacuum art coating is obvious was thickness and hardness. And conclusion, here is open is stability obtained materials with extreme hardness value. For more refractory compound from here, the ratio of hardness to module elastic is close to 1:10, like diamond. For this, the materials must have a nanostructure in macro volume and picostructure, cluster structure inside nanograins. The present results once again show the promising potential of HERE in various industrial applications. Thank you for attention. Please send your question of email. Дякую за увагу.
Thank you very much. Dr. Korban, dear colleagues, who has any question? Raise your hands and I will come to you. Okay, I will ask. Dr. Korban, could you tell me, you showed two types of electrical deposition and one more time another for deposition. Could you show this slide and explain what is the mechanism, why they have different parameters, mechanical parameters? How do you see?
We can hear you very well. Maybe try to.
Could we ask in Ukraine?
Okay, maybe can I have a short question?
Okay, let's try.
Thank you very much for a very interesting presentation. It's a very interesting topic. Okay, okay, thank you. We will write the questions via email, okay?
Okay, we will. Thank you very much for the very interesting report. And right now, it's all agenda before coffee break. So I would like to have a little bit rest for the. Should we start earlier? How do you think? Could I ask Kiev? Should we start earlier if we have right now just only 15:43 and coffee break will continue till the 16:20. Should we start earlier or we will have a break? Because it's all agenda for us and then will be flash poster session.
I think we can try to start at 16 o'clock, but maybe not all participants will be available to join at this time. So we can start, but then we can repeat those participants who were not at their time with us.
Okay, okay. So dear colleagues, we have a rest till 4 o'clock p.m. We are waiting for you, and until this time, have a rest and have a breath a little bit more, yes, for the flash poster session. And dear colleagues who has a poster speech, please be in here at 4 o'clock and wait for your poster because it will be very quickly changing. Okay, be ready.
You are ready. Александр,
Hello? Are you here? Are you hear me? Do you hear me? Sound check. Can anybody hear me? Yeah, somebody hear me. It's great.
Хоть кто-то нас услышал, да? А ну-ка сделай еще раз тогда. О.
Wonderful. So I think that everybody are ready to start flash poster session. Am I right? Dear colleagues, Kyiv, we are ready.
Maybe 1 minute, please.
Okay.
Hello, we can start.
Okay, great. So let's start a flash poster session. And I would like to remind that you have anybody who has a flash poster session has 5 minutes to describe your results. Please, and the first one, Yulia Tishuk, femtosecond laser inductive microstructuring of steel to improve tribological properties. Is Yulia Tishuk here? Dear colleagues, do you hear me or Kyiv, do you hear me?
Yes, we hear you very well.
Okay, very well. And what about Yulia Tishuk? Are you here? Are you online? Yulia Tishuk? Yulia Tishuk? No? Should we switch it and move further? Dear colleagues, or we will wait. If Yulia Tishuk is not present, should we move further or not?
В чем это? Ну, сказали, что у нас слышно. Где первый докладчик?
Should we wait or should we move further to the next one, to the Alexander Moros, or not? And the next one, Alexander Malos, technology of electrolytic plasma polishing for IC 430 and IC 420 steels. Alexander Malos, are you
Good
here?
afternoon, dear colleagues. Can I start?
Yes, you can.
My name is Alexander Moros. I am from Kharkiv National University. Today I present as a result of my research of the technology of electrolytic plasma polishing, or EPP, for IC 430 and IC 420 steels. These materials are widely used in medical instruments, decorative items, and household products, where surface quality play a critical role. However, traditional polishing methods often rely on toxic acids and chemicals, which cause environmental and health problems. Therefore, developing an environmentally friendly and automated polishing process is an important task. Electrolytic plasma polishing is an innovative method that meets these requirements. It used no-toxic electrolytes, low energy, and low automations of the process. In this work, I investigate how temperature and electrolyte composition affect the polishing result for IC 430 and IC 420 steels. The experiments were carried out on the paper 4M installations, which includes a 0.8 cubic meter chamber, cathode temperature control, and power supply operating at 280 volts and up to 120 amperes. The electrolyte contained 3% ammonium sulfate and 2% urea. Samples of both steel size 75 by 25 by 2 millimeters were emitted into the electrolyte and at a controlled speed. Surface rawness was measured using a microgamma profilometer, and surface morphology was studied using optical microscopy. The results showed that the optical parameters are a temperature between 78 and 80 degrees Celsius, and a processing time of 3 to 6 minutes. Under these conditions, the surface rawness decreased by 1 to 5 micrometers, and oxide fumes and contaminants were completely removed. The polished surface of both steels became smooth and shiny, suitable for decorative and medical use. Importantly, the same non-toxic electrolyte worked effectively for both steels, AC 430 and AC 420, which confirms the versatility of the technology. In conclusion, electrolytic plasma polishing using ammonium sulfate and urea solution provides a sustainable alternative for traditional acid-based
Is everything
processing.
okay with your sound?
You can hear me?
Something wrong with your sound, am I right?
You can hear me?
Alexander Moros, is everything okay with your sound? Because we just don't hear you at all. It was written that the dynamic was changed to the earphones.
I have no earphones with dynamics. Now you hear me or no?
I don't hear anything, I'm sorry.
But I am hear you.
And now?
You don't hear anything? Could you hear us?
Yes, I can hear you.
Do you hear us?
Yes, I'm
Alexander
hearing
Moros?
you.
Online is everything okay. Online is everything okay.
Yeah.
People say that they can hear me.
Right now we are hear you.
Okay. You hear nothing that I read?
No. It was just interrupted at the last part.
Okay. Okay. In conclusion, electrolytic plasma polishing using an ammonium sulfate urea solution provides a sustainable alternative for traditional acid-based polishing. It eliminates harmful waste, reduced energy consumption, and produce high-quality surfaces. The method was significant potential for industrial applications, especially in medical, decorative, and household sectors. Further works will focus on scaling up the process and integrated it into continuous production system. Thank you for your attention.
Thank you very much.
I apologize, it's maybe something with network.
Thank you very much for your report. And the next one, Sergei Schwab, experience of welding high manganese steel, ferrum 28 manganese, 11 aluminium, 1.2 carbon. Sergei Schwab, are you here? Are you online? Sergei Schwab, are you online? Sergei Schwab. Sergei Schwab. Baton Electric Welding Institute. Are you online? Maybe we can move a little bit further and then we will back to him. Yes?
Sure.
Sure, so let's move further. Ludmila Nerkova, investigation of stress concentrator in weld on stress corrosion cracking of welded joint H70 steels in near neutral pH solution. Ludmila Nerkova, are you online? Ludmila Nerkova. Ludmila Nerkova. The same, Baton Electric Welding Institute. Are you online? No, she is not. So let's move a little bit further. Yes? And then we will back. Okay? Or we will wait.
Yes, okay.
Okay. Olena Bernikova, features of the microstructure of structural steel after surface treatment by pulsed barrier discharge. Olena Bernikova.
I am online. I am online.
Okay, and what about
Not Olena Bernikova, Olga Mihodu. I am online. Are you here?
Yes, we are. We can do it. We can hear you.
Good afternoon, dear colleagues. Thank you for the opportunity to participate in the conference. The production of metal structures that operate under external loads and in critical applications is associated with the development of new metal processing technologies. Treating the surface of 25 kH GNMT steel using pulsed barrier discharge to improve its mechanical characteristics open up new possibilities for the applications of electrophysical processes in metalworking. The traditional method of hardening such steel involves quenching it in oil at a temperature of 860 Celsius and then tempering it in the air at 190 Celsius. This is an energy-intensive process that requires bulky equipment. Pulsed barrier discharge generates low-temperature plasma on the surface of the metal being processed. The surface of the 4 mm thick plate was treated with pulsed barrier discharge using an electrode system. The photo shows the uniform nature of the discharge between the sample and the dielectric barrier. To reduce the edge effect, the electrode has rounded edges. The pulsed barrier discharge current consists of two main parts, a direct current with the amplitude of 80 amperes and a reverse current with an amplitude of 65 amperes. During a direct current pulse, the average current density through the plate is 0.9 amperes on square centimeters. The electricity consumption of the proposed technology is 1/3 lower. The author researched the effect of pulsed barrier discharge on the structure, phase composition, dislocations, and strengthening of 25 kH GNMT steel. The microstructure of the metal before and after surface treatment was analyzed using transmission electron microscopy. This steel, in its initial state, has a martensitic bainitic structure. The structure consists of temperate martensite up to 60% and lower bainite up to 30%, with a uniform distribution of dislocation density and a small amount of quenching martensite, 5%, and upper bainite, 5%. After treatment at a depth of up to 2.2 millimeters from the surface, the microhardness of metal increases by 20%, and the phase composition, substructure parameters, and dislocation density change. In the surface layer, up to 300 micrometers from the treated surface, a laminar martensite and lower bainite structure is observed, with a volume fracture increase to 50% and an absence of hardening martensite and upper bainite, accompanied by thinning of the lamellar component. The dislocation density in the structural components increases, forming a cellular substructure. Research has shown that treating the surface of the 25 kH GNMT steel with pulse barrier discharge technology strengthens the metal and improves its resistance to cracking in the treated area. Using pulse barrier discharge to treat the surface of this steel could form the basis for developing a number of surface treatment technologies aimed at extending the service life of metal materials. Thank you for attention.
Thank you very much. Dear organizers, should we ask about the previous report? Should we ask about Yulia Tishuk, Sergei Schwab, and Lyudmila Nerkova?
They don't know.
Yulia Tishik, I'm here.
Great. So maybe we can move to the Yulia Tishik back.
Okay. Okay, can you see show?
Yulia
Oh,
Tishik?
yeah. No, it's not mine.
Yeah, femtosecond laser reproductive microstructure of steel to improve tribological properties.
Yeah, thank you. Good afternoon. My name is Yulia Tishik. I am 40-year student at Lviv Polytechnic University Department of Applied Physics and Nanomaterial Science. I would like to inform you about our study of femtosecond laser induction microstructure on 17720 steel, which aims to exchange its tribological properties. This research was carried out in collaboration with our colleague from the Polytechnic National University, Karpenko Physics Mechanic Institute of National Academy, the National Research Center Kharkiv Institute of Physics and Technology, Ukrainian Energy Machine, and Laboratory Novi Nano. As the development of mechanical engineering requires creating increasing reliable and well-resistant components, improving tribological properties remained a highly relevant task. Steel 17720 is widely used to seal that operation in friction union and can withstand temperature up to 450 degrees Celsius. Our study aimed to elevate the tribological properties of 17720 steel after the formation of microstructure on its surface under lubrication and lubrication condition. The typical chemical composition of steel is shown in the table. For lubrication, we use fine molybdenum disulfide powder. The value of the friction coefficient where the meter and where of the tracks was determined using a profilometer, and the volumetric wear of the plate and balls was calculated. Microstructures were produced using a femtosecond laser furrows. Detailed parameters of the fabricated mesh structure and lips, as well as their imaging, are shown in the figure. The specific wear rate was calculated according to the given formula. For compassion and treat steel was also tested. The table presents surface roundness values after microstructuring. The figures clearly show that with the use of molybdenum sulfide, both the wear tracks width and the overall wear decreased in all cases. When a poly mesh type structure with molybdenum sulfide lubrication, wear was reduced by 2 order magnitude. Conclusion. Femtosecond laser microstructures enable the precise formulae of ellipse and mesh pattern without thermal damage, efficiently controlling friction relative surface properties. The addition of molybdenum sulfide stabilizes the friction coefficient and at approximately 2/10 and significantly reduced were due to the formulation of stable tribofilm. The best results were obtained with mesh structure in combination with molybdenum sulfide lubrication. Minimized place wear by 2 orders of magnitude and substantially reduced counterbody wear. Thank you for your attention.
Thank you very much. Sergey Schwab, are you online? Sergey Schwab. Людмила Ныркова, are you online? Людмила Ныркова, are you online? Людмила Ныркова. No? The next one, Igor Navolnev. Igor Navolnev, are you online? Igor Navolnev. Are you online? Igor Navolnev? No?
We
The
are
next
here.
one. Yeah, you are
We are
here?
here, да.
Hello.
Great.
Me?
Igor Navolnev?
Yes, yes. Are you hear me?
Yes, we are.
Okay.
We do it.
Good
We
afternoon.
hear you.
Good afternoon, dear colleagues. My name is Igor Navolnev. I am a PhD student at Invest Polytechnic. Today, I am presenting the key findings of our study of energy implication of transition of surf-act modified iron or concentrate during pellet induration. The research is based on industrial trails, conduction, the leading mining is processing enterprise in the Кривой Рог region. Да. Вы пролистали назад. I'm so sorry. Вот. Назад. Be back. I'll be back. Iron pellet production is critical stage in metallurgy, but is highly energy intensive. Drying alone requires 0.93, 1.74 kilowatt-hour per kilogram on removed water, significantly impacting cost and emissions. We faced a transition from enterprise concentrate to a thinner, more dispersed concentrate from Enterprise B. To improve pelletizing, Enterprise B concentrate was treated with nonic surfactants, which enhance wettability and aggregation. However, with increases hydrophility and necessitating addition monitoring of a change mix. As shown in a problem action result diagram on the slide, this leads a high monster, altered rheological properties and dialing instability, increasing electricity and natural gas consumption while reducing productivity. We conducted 8 days trials on conveyor type firing machine with 336 square meters grand area and capacity of up 300 ton hours. Day first and second used Enterprise concentrate for Baseline metrics, while another day Enterprise B SAS tried concentrate. We monitoring hourly parameters bentonite consumption, green pellet, monster straight, practical size distribution, bed height, and chamber pressure. Energy consumption was measured using Elster BK G1000 gas meters and NIC 2303 AP3 electric key meters. Regression models were built using data analysis and predict energy consumption and productivity. So monster and productivity energy escape factor with R squared is great 0.99 confirming model reliability. Is the table on slide show the outcomes productivity drop minus 9.55%. With a minimum on a 3-day transmission, specific electricity consumption rose plus 17.73% and natural gas plus 33.25%. Bentonite consumption is carried plus 5.43% and green pellet moisture from plus 6.15%. There are diagram on the slide illustrated how the high dispersion of the Enterprise B concentrate recurs more moisture, driving up energy cost. So conclusion, SAF improves pelletizing for dispersed concentrates, but raise green pellet moisture by 6.15%, electricity consumption by 70.73%, and gas by 33.25%, while reducing productivity by 9.55%. To enhance process efficiency, running games and SAS dosage should be optimized. These findings are critical for energy management in metallurgy when transitions to new material. Thank you for your attention.
Thank you very much. And if Sergei Schwab here, Sergei Schwab, Lyudmila Nerkova, are you here? Lyudmila Nerkova? No? Okay, the next one, Ivan Manachin. The interaction of the components of the injected two-phase flow with hot metal during injection desulfurization in the ladle.
Afternoon, dear colleagues. I would like to present you a short report about our scientific report, the interaction of the components of the injected two-phase flow with hot metal during injection desulfurization in the ladle. As you know, secondary furnace desulfurization of hot metal has become reliable and important link between blast furnace production and steel making. The out-of-furnace desulfurization of hot metal with various dispersive desulfurizing reagents due desire ensures the most complete removal of hot metal sulfur in the shortest period of time. The actual results of the industrial application of out-of-furnace desulfurization indicate that the practical results of the application raise a number of cases and are not stable enough. The studies we carried out of calculated and cold transparent physical models, magnesium, lime, and calcium carbide were evaluated as desulfurization reagents. Based on an actual results and physical modeling and subsequent calculations, an improved extension was formulated for determining the length of the gas jet and depth of the immersion, and depending on the parameters of injection through submerged length. The processes of interaction between gas and solid phases in the near length zone during the ladle desulfurization have been studied. It is shown that during the injection desulfurization, gas component of the flow stops in directional movement in the melt for up 80 millimeters. Solid particles continue to move in the bubble and hit the surface of this cavity. They assess the further movement, the particles through the gas cavity melt boundary and depth of penetration of particles into a liquid was calculated. The motion of the particles in the melt can be described by the equation that we show on the slide, and arrange for the condition of vertical motion of a particle from top to bottom with a given initial velocity up to the complete stop of the particle. Nomograms are given and determining the specific parameters. Recommendations are given on the parameters of injection of magnesium and lime. Thank you for your attention.
Thank you very much. The next one, Maria Kobylinska. Maria Kobylinska, are you here? Are online? Maria Kobylinska, are you online? Maria Kobylinska? No? The next one, Svetlana Gubenko, the influence of laser treatment on the formation of hydrogen-induced microcracks near inclusions.
Dear colleagues, the topic of our poster presentation is the influence of laser treatment on the formation of hydrogen-induced microcracks near inclusions. The problem of steel endurance in hydrogen-containing environments has remained actual for many years. It's known that with decreasing temperature, the solubility of hydrogen in the liquid and solid steel decreases abruptly during crystallization and allotropic transformations and smoothly within each modification. The hydrogen released in this case can form microcracks inside the metal as well as in the surface layers of metal blanks and products. In our works, we presented the results of a study of the tendency of nonmetallic inclusions to cause hydrogen cracks at inclusion matrix interface boundaries in the steels. The goal of this work was to establish the effect of preliminary laser action on the formation of hydrogen-induced microcracks in the surface layers of steel products. Samples of different steels with various types of nonmetallic inclusions were subjected to isothermal holding in the atmosphere of technical hydrogen for 2 hours at different temperatures and pressure of hydrogen. Look at table, please. Some of samples were subjected to laser treatment on GOS-30M unit before annealing in a hydrogen environment. Pulse energy was 20-25 joules. Action time was 10 in -3 seconds. The number of hydrogen-induced defects were determined after the samples were exposed to air for 200 hours. Look at table, please. The results of the studies indicate that almost all parameters of the formation of hydrogen-induced microcracks that arise in the surface layers of the samples near sulfides after laser treatment have values 30–40% lower than similar indicators for the inclusions in the internal sections of the samples, and also 25–30% lower than similar indicators for inclusions in the surface section of the samples that were not subjected to laser action. Local microwelding that occurred along the sulfide matrix interface boundaries under laser action contributed to the increase in the cohesive strength of these boundaries, which had decisive effect on the process under study. Obviously, during laser treatment of steel products, along with strengthening, an additional effect is manufactured, an increase in the hydrogen resistance of steels, which is important, is in cases of operation of these products in the hydrogen environments. Thank you for your attention.
Thank you very much. Evgeny Stefan. Evgeny Stefan, are you online?
Online, thank you.
Okay, so the next one, mathematical modeling of structurally inhomogeneous porous materials forming processes.
Good afternoon to everybody. Greeting from Kiev. Thank you very much for the opportunity to join this wonderful scientific event, International Material Science Conference. I would shortly present some theoretical results which devoted to mathematical modeling of porous material forming processes. This work was co-authored with my colleagues from Francevich Institute for Problems of Material Science. The main task of our joint work is to create an instrumental computer system, software type, for conduction numerical experiment to study process of shaping and densification of porous materials. Such materials may contain not only traditional pores and also rigid particles. Unlike to the most well-known software versions, the model present here is taking into account the macro non-homogeneity of matrix phase. In particular, it is considered as composite containing rigid inclusions which can interact with matrix material. The analytical part of mathematical model is based on the system of equation that shown on this poster of the theory of plasticity of the porous material. This theory was created by scientific school of Francevich Institute of Problems of Materials under the leadership of academician Mikhail Stern. For effective practical use of the proposed theory, a set of algorithms based on the finite element methods has been developed. Algorithmic models by the finite element methods application for rigid plastic and elastic plastic behavior of powder materials presented. The main algorithmic blocks were implemented in the modern finite element software versions. The effectiveness of the practical application of the developed instrumental system is demonstrated by some modeling examples that also presented on this poster. I show only three based examples. First of these examples is the twist extrusion, is a forming process that allows obtaining the ultrafine grain structure of the material as a result of severe plastic deformation. It was found that the presence of back pressure allows preventing the growth of porosity and to improve the uniformity of its distribution. With an increase of the number of processes passes, the overall level of accumulated deformation increased significantly. In this case, after the first process pass, it is possible to obtain sample with almost maximum density. The second example devoted to compaction of biporous materials. Biporous materials include powders whose particles have their own porosity. A combined modeling method was used, combined continuous and discrete approaches. So the behavior of the powder was considered as the two structure levels. The deformation of each porous particle was considered within the framework of the continuous approach. The relationship of the rigid plastic porous materials model and finite element method was used. According the given dispersion of the powder blanks was considered as a set of a specific number of such particles interaction with each other in the presence of contact frictions. The two-side pressing numerical modeling made it possible to establish the influence of the pressing scheme on the workpiece porosity distribution, as well as to determine the particle final shape. And the last example devoted to forming process of porous materials with rigid inclusions. Two deformation schemes of composite materials blanks, porous matrix and hard inclusions were considered. One, the free draft that shown on the process and indentation by the spherical pen that is not shown here. The matrix material is an aluminum alloys which contains inclusion materials on the base of silicon carbons. The plane deformed states straining was considered and symmetry properties were taken into account. Analysis of the modeling results showed that the stress-strain state of the blank is similar to the state of the deformed blank that does not contain hard inclusions. At the same time, the presence of the hard inclusions introduced a number of features. Maximum stresses arise in areas near the inclusions and in them themselves. In this area, separations of inclusions from the matrix is possible. The stress-strain state of blank is affected by the location of the inclusion in this volume, as shown on these pictures. Obtained results can be also used for prediction of the given phenomenon in framework of the presented general model. Thank you for your attention. That's all.
Thank you very much. The next one is Viktor Goncharuk. Are you here online? Viktor Goncharuk. Viktor Goncharuk. Viktor Goncharuk, are you online? Okay, and the next one.
Yes.
Yes, you are. Viktor Goncharuk. Okay. Analytical description
my
of
name,
a high.
My name is Mykola Efimov. I make this report instead of Viktor Goncharuk.
Okay.
Good afternoon, dear colleagues. Let me present the report about analytical description of the high velocity penetration process of rigid cylindrical projectile into a target. In the problem of high velocity interaction between an indenter and material, the calculation of the critical penetration velocity is of significant scientific and practical interest. The penetration process of a projectile through a target shapes much in common with the indentation process of a material by a rapid indenter. In this work, based on the authors' developed concept for the indentation process, the problems of calculating the critical penetration velocity using experimental results obtained from indentation test is considered. In the particular solution of the Alexeyevsky equation, the expression for the critical penetration velocity of the undeformable projectile of a semi-infinity target is derived. This velocity depends on the static penetration resistance of the target materials, as well as the projectile's length and density, and the target's density and thickness. For an elastic ideally plastic material, resistance of the target materials can be estimated using a Hill approach. However, as shown, a more accurate estimate of the resistance of the target materials required considering the target materials plasticity, namely plasticity characteristic delta H, which can be determined through the indentation experiments. The product of resistance of the target material on plasticity characteristic isolated the part of resistance due to the plastic deformation of the materials under a kinetic indenter. Ballistic test on aluminum alloy target from alloy 5083 2139 and AZ31 alloys using two types of indenter. First indenter with diameter 7 and late 27 millimeters, and second indenter with diameter 12 and length 43 millimeters, yielded critical penetration velocity values for different targets' thickness. A comparison of experimental and calculated critical penetration velocity values showed good correlation with an error below 3%. As a result, a simple analytic formula for calculating of critical penetration velocity was developed. This formula contained no empirical coefficient and required minimum data about the projectile and target materials. This significantly simplified and speed up the process of creating protective elements due to a significant reduction in the number of experimental tests. Thank you for attention.
Thank you very much. And the next one, Viktor Kurilovich. Are you online? Viktor Kurilovich.
He is here.
Great. Improvement of a friction machine for studying the tribological characteristics of materials and coolings at high temperatures. High temperatures.
Good afternoon. Today I'll present our work on improving the friction machine to study material wear and friction at high temperatures. The challenge is clear. As materials operate in hottest environment, we need better tools to test them. Exciting machines often struggle with temperature stability and data collection, which can make test results unreliable. Our solution was to develop an improved universal setup. We based it on the laser for speed control and integrate a muffled furnace that can maintain a stable 60 degrees Celsius. The core of our upgrade is custom data acquisition system using on Arduino, which collect data from sensors in real time, ensuring high accuracy. They allows us to conduct tests under demanding conditions, loads up to 10 MPa and sliding speed up to 10 meters per second. We can now reliably record the friction coefficient, temperature, and pressure at the test is happening. The impact is significant. This setup provides a reliable basic for developing new wear-resistant material for extreme condition. Our methods is versatile and can be applied in critical industries like energy, aviation, and mechanical engineering. Thank you for your attention.
Thank you very much. The next one, Danila Korolenko. Are you online? Danila Korolenko. Danila Korolenko. Are you online?
Yeah, sure, I'm here.
Great. A computer method for studying grain misorientation of material science problems.
Yep. Good afternoon, everyone. My name is Daniil Korolenko, and I'm PhD student of Proton Electric Welding Institute of the National Academy of Science of Ukraine. Within my job, I focus on the microstructure analyzing of welded joints, specifically on determining grains misorientation in the weld metal. To address this problem, I developed my own computer program based on Python and OpenCV library. The program used Hawk method and PCM method for analyze optical images of the weld microstructure. The algorithm first converts the original microstructure image into a monochrome format to eliminate color and lighting effects. Then, using edge detection and counter analysis, it identifies individual grains within the weld metal. Each grain is processed using the Hawk transform, the principal component analysis to determine its main orientation angle. The program then compress neighborhood grains and calculates the angular difference of misorientation and builds a statistical distribution of these angles. This allows us to visualize how grain orientation varies across the weld, detect areas with excessive misorientation, and estimate the overall structure quality. In simple terms, the software automatically converts a regular original photo into a quality regional orientation map. Some web about Hawk method and PCR method what I used. The Hawk method or Hawk transform is a computer vision method that helps to detect straight lines or shapes in the image. In my case, I used it to find the boundaries of the grains in the weld microstructure. By recognizing the detection of these boundaries, we can estimate the main orientation of each grain. The principal component analysis or PCR method, as I said, is a mathematical method that finds the dominant direction in a set of points. In this case, inside each grain. It analyzes the shapes of the grain and determines the angle of its main axis. Combining this both methods allows us the program that could to detect not only where the grains are, but also how they are orientated relative to each other. This is the key step for calculated grain orientation and misorientation across the weld. Moreover, the program was able to identify the percentage of grains with misorientation exceeding the threshold value, a parameter that directly affects the weld strength and reliability. Thanks for your attention.
Thank you very much. The next one, Galina Molchanovska. Galina Molchanovska, are you online?
Hello, I am substitute Galina Molchanovska.
Okay, the report is X-ray diffraction studies of the fine structure of multi-component alloys of the system ferrum, chromium, molybdenum, vanadium after rotary forging.
The studies present the result of X-ray diffraction studies of samples of an experimental multi-component alloy of the chrome molybdenum vanadium system. The alloy was subjected to rotation forging, which caused a gradient of microstrain tensile and compressive stress across the cross-section of the sample. Subsequent of heat treatment improves the structure and relieves microstructures. The X-ray spectrum of the ferrum chrome molybdenum vanadium alloy is characteristic of BBC Aeron. The unit cell parameters alpha equal 0.2875 nanometers, which particularly correspond to the parameters of unalloyed iron and indicate the absence of solid solution based on the ferrite phase. Lines of flow intensity may belong to carbides of iron, chromium, or molybdenum. Studies of the fine intergranular structure revealed the presence of two phases which varying degrees of defects, like alpha 1 and alpha 2. The calculated fine structure parameters indicate that alpha 1 phase is significantly defective. The dislocation density for the alpha 1 phase is 92.31 centimeters. For alpha phase, it's rho in equal to 0.004 centimeters mean square. Microdeformations respectively is A1 equal to 25.33 and E2 is equal 7.59. The size of CSR for alpha 1 is 12.73 nanometers. For alpha phase is 35.1 nanometers. However, the ratio of microstructure for both phases is close in value and indicates a uniform distribution of dislocation. It can be assumed that the alpha 1 phase is the result of the state of the fine structure at the time of deformation phase. Alpha 2 is state of the substructure as a result of sequences annealing of phase alpha 1. The formation of a solid solution based on the ferrite structure were not revealed. The mechanical properties are due to the deformation effect of rotation forging and heat treatment. Thank you for your attention.
Thank you very much. The next one, Natalia Zakharova. Natalia Zakharova, are you online?
Speaker is here.
Okay. Effect of chemical composition and heat treatment on the mechanical properties and electrical conductivity of aluminium, magnesium, silicon, and alloys with a magnesium-silicon ratio of 1.
Well, good afternoon. My name is Alexey Muzika, and I will present our short report as a co-author. Aluminum ranks second only to copper in electrical conductivity, yet it is approximately 4 times cheaper. This makes aluminum, magnesium, silicon alloys attractive for electrical applications due to their potential for both dispersion and strength hardening. However, the magnesium-silicon ratio strongly influences dispersion strengthening. This study aims to identify suitable heat treatment regimes for aluminum, magnesium, silicon alloys with a magnesium-silicon ratio of 1. An ingot of respectful alloy was produced by rapid solidification. Using two-step extrusion at 400 Celsius degrees, followed by drawing at 200 Celsius degrees, wires with a diameter of 4 millimeters were obtained. The wires underwent 2 heat treatment routes. Heat treatment 1, solution treatment at 530 degrees and aging at 140 degrees for 8 hours. Heat treatment 2, solution treatment at 560 degrees and aging at 175 degrees for 6 hours. The microstructure was analyzed using optical microscopy and scanning electronical microscopy, while mechanical properties and electrical resistivity were evaluated. The S-cast structure consists of a solid solution of alpha aluminum and crystallization origin intermetallics, exhibiting a hardness of 466 MPa. In the wires after drawing and heat treatment 1, no recrystallization was observed. Before heat treatment, the structure contained aluminum, magnesium, and silicon, and aluminum, ferrum, and silicon phases. After heat treatment 1, only aluminum, ferrum, silicon particles remained. After heat treatment 2, a recrystallized structure formed with the fine aluminum, ferrum, magnesium, silicon particles appearing within the grains, identified as aluminum 12, ferrum, magnesium 3, silicon. According to mechanical testing, the experimental alloy after heat treatment 2 demonstrates mechanical properties nearly comparable to those of the reference alloy AD31, specifically showing high values of yield strength 140 MPa and UTS 200 MPa, as well as almost twice the ductility compared to AD31. At the same time, due to the microstructure formed during heat treatment 2, the alloy achieves an electrical conductivity of 41 IACS compared to 40% IACS for the AD31 alloy. Thus, the investigated alloy, after solution treatment at 560 degrees followed by aging at 175 degrees for 6 hours, provides a satisfactory balance between mechanical strengths and electrical conductivity, making it a promising candidate for electrical engineering applications. Thank you.
Thank you very much. The next one, Inna Kirian. Inna Kirian, are you online?
Hello. Inna Kirian is absent. Presentation will be made by me, one of co-author, Alexander Rud. So, can I start?
Yes, you can.
Yes, thank you. Our presentation in title
Is everything correct with the voice? Because it's interrupting sometimes. The voice is interrupting. Right now we don't hear anything. Kiev, can you hear us?
Of Inconel 700.
Sometimes.
So it's our problem, yes? It's a problem from Dnipro, or you can...
It's problem from...
It's a common problem.
Alexander.
So we don't hear anything. I'm sorry. Mr. Alexander, Mr. Ruth, we don't hear you.
We too don't.
Unfortunately, we don't hear you. It's something wrong with your voice, with your connection, I think. Alexander Ruth. Can you hear us? Alexander Ruth. We don't hear you. I'm sorry. Alexander. Alexander, we don't hear you.
Can't hear you. I think you have problem with your apparatus. Yes.
No, it's your problem. It's your problem. Everybody can't hear you.
It's your.
No, it's not our problem. Kiev said that they could hear us. Couldn't hear you.
Well, what about this? What about this?
Right now, it's great.
No, it's great. Yes, everybody. Well, I restart. Hear me.
Our presentation entitled. One moment, please.
Oh, no.
Well. Do you hear me?
Yes, we do.
Yes.
Yes. Our presentation entitled Advanced Processing of Inconel 718 net shape products via MIM, the binding, sintering, and heat treatment insights. Nickel-based alloys such as Inconel 718 are widely used for turbine blades production. They have excellent strength and corrosion resistance at high temperatures, up to 700 centigrade. But traditional methods of making these parts include many steps: hot deformation, cutting, and machining. These processes cause a lot of materials waste. All this makes production expensive and time-consuming. MIM technology, metal injection molding, offers a modern solution. It combines powder metallurgy and plastic injection molding. Fine metal powder is mixed with a binder to form a feedstock. The feedstock is injected into a mold to make a part with the desired shape. Then the binder is removed and the remaining compound is sintered at high temperature to form a dense metal part. This reduces material waste and production cost. MIM works well for many steels and ceramics, but for Inconel it still needs optimization, especially in the debinding, sintering, and heat treatment stages. In the present study, spherical Inconel powder was obtained by gas atomization and mixed with a poly-MIM binder to prepare feedstock granules. Following the MIM process, the feedstock was heated to 200 centigrade and compacted under 100 megapascal pressure into preforms of different turbine blade geometries. The binding process was carried out in two stages. During the first one, the green compacts were washed in hot water to remove the water-soluble binder components. Microscopic examination revealed the formation of thin binder layers and hollow voids between the powder particles. In the second stage, the compacts were gradually heated in vacuum to 800 centigrade to remove the remaining binder residues. After that, sintering was performed in argon atmosphere. In conclusion, the conducted research demonstrated that metal injection molding is a promising and cost-effective approach for manufacturing Inconel turbine blade with complex geometries and excellent mechanical properties, suitable for advanced high-temperature applications such as aircraft engine parts. Thank you for your attention.
Thank you very much. The next one, Galina Maximova. Are you online? Galina Maximova.
Hello, same situation. I am replace Galina for this.
Okay. Microstructure and phase compositions of high alloys based on the tungsten carbon radium system.
So, yes, thank you. The experiment had alloy of wolfram carbon radium system contains radium up to 2% weight and is alloyed with cobalt, iron, and chromium in total amount up to 1.5% of weight. The alloy was obtained by compaction and elevated temperature and high pressure. The density of composite is 98%. Micro hardness is from 28 to 30 GPa. The surface for structural studies was subjected to electrochemical etching at 0.4 mol/liter sodium hydroxide solution at a voltage of 10 volts. The microstructure of alloy is homogeneous. The grains of tungsten matrix are ellipsoid with size from 10 to 20 nanometers. Imperative and distributed evenly in the tungsten grain and at their borders in the form of solid solution. Tungsten monocarbide is present in two crystalline modification, cubic and hexagonal, and is uniformly distributed in the triple joints of the matrix. The average grain size of tungsten monocarbide is from 2 to 5 times smaller than the average grain size of the tungsten matrix and is from 2 to 4 microns. The grains of tungsten monocarbide currently border the grains of the tungsten matrix and have a shape close to cubic. In some images, wolfram and wolfram carbide grains have the same structural contrast, since they have the close atomic mass. Rhenium is not distributed uniformly in the alloy in area with increased rhenium content. The tungsten grain size is minimal. Thank you for attention.
Thank you very much. The next one, Marina Bulanova. Marina Bulanova, are you online?
She is here.
Great. Structure and properties of ternary compounds in the zirconium, nickel, titanium, and hafnium, nickel, and titanium systems, subsystems.
Hello, colleagues. Let me show you our last results. Ой, она вместила. Нет, this one. Thank you. Let me show you our last result concerning two ternary compounds in the systems shown in the title. So first one is the ternary compound in the zirconium titanium nickel system. It was found in 1966 by Van Vogt, and then its existence was confirmed in 1987. Since that, this compound was forgotten, and nobody of the researchers mentioned it until these times when we reopened this compound. It is shown here in the the compound has 75% of nickel and has the homogeneity range elongated along this isoconcentrate. Near it, we can see the homogeneity range of the binary titanium nickel 3 compound. These homogeneity ranges are very close, and the two-phase region between them is extremely narrow. We'll find that compound melts incongruently, forms from the melt with participation of the binary compound. And possibly due to this, it always nucleates on the grains of the binary compound. This is one interesting thing with it. It can be seen in the microstructure, the upper microstructure here. And another interesting thing with this compound is that if it is present in eutectic alloys, then eutectics does not look really eutectic. It looks like the frozen melt. But if it happens that we anneal such an alloys, then eutectic structure becomes obvious. So we can conclude that presence of this compound provokes amorphization of the samples. Another ternary compound in the system with hafnium, it was found by us for the first time. It was shown that compound melts congruently, and it is seen from the microstructures of S-cast alloys. It also exists after annealing at 1000 degrees centigrade. Its crystal structure was resolved, and the details are shown here. It is interesting that the X-ray diffraction pattern here is very similar to those of the air phase of the titanium nickelide. It is one interesting thing. And another one is that in the microstructure, we can see the twinning-like structure, which is also can be observed in titanium nickelite. And that's why we've decided to measure some physical mechanical properties, and we measured micro hardness of the alloys of the compound of two compositions. And we can see that it is very high. It is more than 1000 Ash-mu. So the work with these compounds and with the alloys containing these compounds is in progress. Thank you for your attention.
Thank you very much. The next one, Oksana Vlasova. Are you online? Oksana Vlasova. Oksana Vlasova.
Hello, I'm substitute also Oksana Vlasova today.
Okay, influence of the structure of the lamination layer on the technical characteristics of the bimetallic composites copper ferrum.
Thank you. In research studies, the cuprum-plumbum steel composite obtained by pouring bronze layer onto cooled steel surface. The method allows to reduce lead liquid and use the accelerated cooling to obtain uniform distribution of lead in laminating layer and to increase its anti-frictional properties. Optical and diffraction method have established that the cuprum-plumbum laminating layer has a uniform thickness of 382 microns. The layer is made of lead of bronze, with the lead contains of about 20% in chemical composition. Lead does not dissolve in copper and present in the alloy in the form of grains of various sizes, uniformly distributed in the copper matrix. Tin and zinc with the total content of up to 5% are in solid solution and form a series of chemical compound with copper located along the grain boundaries. The micro-hardness of layer varies from 280 MPa for lead grains and up to 1030 MPa for copper grains and solid solution. Of the laminated layer is 645 MPa. The presence of a good metallurgical bond at the interface between the cuprum-plumbum laminated layer and the base alloy was established. The chemical distribution of element at the boundary between the layers shows the penetration of iron into the sublattice of laminating alloy to deep up to 5 nanometers. The presence of tin and zinc increase in the penetration of iron up to 10 nanometers. The presence of plumbum-rich zones in the laminating layer significantly increase the wear resistance and self-lubrication of bimetallic composite, improving its thermal stability and as well as anti-frictional and anti-seized properties. Thank you for your attention.
Thank you very much. The next one, I think yours too.
Yeah.
Microstructure and phase composition of tungsten, cobalt, argentum, copper, bimetallic layered composites on low alloy steel products.
The object of study is composite layers of wolfram, argentum, cuprum placed by electric arc centrifugal method on the working surface of steel. The outer working layer is formed by a hard alloy wolfram cobalt with minor technological improvements of iron, photochrome, phosphorus, and sulfur. The hard alloy layer has a uniform thickness of 1046 nanometers. The microstructure is formed from tungsten carbide measured from 0.4 up to 3.2 nanometers, located in cobalt matrix. The microhardness of the layer varies from 3.0 up to 11 GPa. The intermediate argentum cuprum layer is formed by an alloy of silver and copper, has clearly defined boundaries on the side of the wolfram cobalt hard alloy and one outside of the steel matrix. The microstructure of heterogeneous and is formed by a solid solution of copper and silver and aesthetic with microhardness from 350 up to 850 MPa. The thickness of argentum cuprum layer is 184 nanometers and remains virtually unchanged throughout an entire sample. The experimental result shows that the bimetallic composite has a good bond between wolfram cobalt and argentum cuprum alloys, which is achieved by the penetration of cobalt into the sublattice of the solid solution of the argentum cuprum alloy by several micron layer and is uneven along the interface. The interface has no defects of exhaustive deformation of the layer composite. The distribution of elements at the argentum cuprum steel layer boundary shows that presence of iron in argentum cuprum layer to depth of approximately from 3 to 4 nanometers, which ensured good adhesion and of the layer at the interface and high technological characteristic of layer composites. Thank you for attention.
Thank you very much. The next one, Denis Kukusta.
He is here.
Great. Energy band structure and resonant inelastic X-ray scattering in 5D3 osmosis.
Good afternoon. I would like to present the results of our recent calculations. So, the object of our investigations were chosen sodium osmium oxide, cadmium osmium oxide, and transition metal oxide, calcium lithium osmium. Their crystal structure are shown here. You can see that in all the compounds, osmium atoms stay in the oxygen environment and are surrounded by octahedra. The resonant inelastic X-ray scattering spectra were obtained in experiment and are shown in this column. Basically, you can see that they have rich peak structure, and our main purpose of the investigation was to fit the spectra obtained in experiment and in calculations. This fit allowed us to find the value of effective Coulomb energy correlations. For the first and the second compound, this value was found to be 1.5 electron volt, and for the third compound, it's equal to 1 eV. And this low value can be related to relatively low concentration of osmium atoms in this compound. So once we have estimated the value of Coulomb correlation energy, we can calculate the partial density of osmium state. They are quite typical and shown here in this column. You can see that T2G band is split by Coulomb interaction onto lower Hubbard band and upper Hubbard band. Each state they stay at much higher energies, and the states below T2G lower Hubbard band are formed by so-called tails of oxygen states that appear due to hybridization with osmium states. Calculations allow us to find out the nature of each peak shown in this RIX spectra. We conclude that the first peak, it appears from transitions from lower Hubbard band to upper Hubbard band. The second peak appears due to transitions from lower Hubbard band to EG state, and the third peak appears due to transitions from tails to upper Hubbard band. Once we confirmed this band structure, we can realize that only in one compound, namely in sodium osmium oxide, is so-called G-effective one-half state exists, while in another compound it seems to be suppressed due to so-called quenching of orbital moment on osmium atoms. So thank you.
Thank you very much. The next one, Ivan Luzhny. Are you online? Ivan Luzhny.
I am here,
Hello.
but the speaker will be Igor.
Yeah, I want to present this research.
Okay.
Good afternoon, dear colleagues. I'm glad to see you today. I would like to present the result of our joint research, which took place at the Frantsevich Institute for Problems of Material Science, National Academy of Science of Ukraine. The topic of our research is called electronic structure of the rhombohydride carbide phase tantal for carbide 3 experiment and theory. And most transition metals, carbides, are non-stoichiometric compounds crystallizing with high symmetry FCC and HCP structure. Carbides of the metals belonging to the 4 and 5 groups of the periodical table. Of great interest because they form intermediate phases in the region of compounds between monocarbides processing FCC structure and hemicarbides with RCP structure. These intermediate phases are known to be superstructure with a common formula of the HMCN p-type in Jagodinsky-Witkov symbols, where H and C are the staking sequence of the hexagonal and cubic metal layers, respectively. Unit cells of the HMSN p-types superstructure belong to either hexagonal or rhombohedral trigonal system. Interestingly, that such superstructure process big values of the CH or AH ratio. In the present work, we report on experimental studies employing the X-ray photoelectron spectroscopy and X-ray emission spectroscopy methods, as well as theoretical calculations within a density functional theory framework of the electronic structure of the rhombohedride phase tantal for carbide 3. The calculation carried out using the quantum espresso package. The present experimental and theoretical data indicate that a strong hybridization of the 5D and carbide to p electronic states, is characteristic of the electronic structure of the rhombohedral phase tantal 4 carbide free, and the charge transfer occurs from tantalum atoms to carbon ones. Compares with the cubic tantalum carbide and tantalum carbide 0.75 carbides indicates that the binding energy of the tantal 4F core level spectra is smaller in the rhombohedral phase tantal carbide 4 and 3, as compared to those of the cubic tantalum carbide X carbides. This fact indicated that the metal constituent of the chemical bonding is rather high in the rhombohedral phase tantal 4 carbide 3. In the case of cubic tantal carbide 0.75 and rhombohedral tantal 4 carbide 3. Carbides now subband is formed, which is absent in tantalum carbide in the near Fermi region of the XPS value band spectra. Thank you for attention.
Thank you very much. And the next one, Olena Rokitska. Are you online? Olena Rokitska. Olena Rokitska.
Yes, I'm online.
Great. Oxidation of niobium alloys, niobium 7 molybdenum 1.5 zirconium 0.8 carbon, and niobium 10 chromium 7 molybdenum 12 titanium 0.8 carbon at 1000 degrees.
Good evening, good afternoon, dear colleagues. My name is Olena Rokitska, and I am pleased to present our investigation about oxidation of niobium alloys along with molybdenum, zirconium, titanium, chromium, and carbon at 1000 degrees Celsius. Future aerospace applications require advanced metallic materials for use at temperature over 1000 degrees. Refractory metals and alloys, which their melting points exceed 1800 degrees, good high temperature strength and creep resistance, high thermal conductivity, and low coefficient of thermal expansion are considered for such application. Unfortunately, many of the currently available refractory alloys have a poor oxidation resistance above 800 degrees and have higher density. Among the currently available refractory alloys, only niobium alloys are ductile at room temperature and may have density below 10 grams on centimeter in 3. Therefore, the search for new composition of niobium alloys with improved resistance to oxidation is relevant and promising area of research. The alloys were prepared by vacuum arc melting from high purity metals, and fast composition was conducted by using diffractometer Rigaku Ultima 4 unit operated at quantum alpha radiation. In SK state, both alloys have a body central cubic crystals. The microstructure of the studied alloys is shown that in addition to the body BCC solid solution, the presence of 0.8 atomic percent carbon led to the precipitation of zirconium carbide, zirconium C, inside the grain in the alloy niobium 7 molybdenum, 1.5 zirconium, and 0.8% carbon. But in the niobium 10 chromium, 7 molybdenum, and 12 titanium, and 0.8% carbon, on the grain boundary we may observe a static structure. Probably it's DCC and fuzz lava T from 2, and also is carbide TC within the matrix and at grain boundaries. The oxidation behavior of oils at 1000 degree are significantly different. The alloy niobium 7 molybdenum 1.5 zirconium 0.8 carbon will exhibit a high oxidation rate despite the presence of zirconium, which is known to significantly reduce oxygen solubility in binary niobium-based alloys. In this case, however, zirconium did not have a noticeable effect on the oxidation of this alloy. During oxidation at 1000 degree for 3 hours, the niobium 7 molybdenum 1.5 zirconium 0.8 carbon alloy underwent catastrophic oxidation accompanied by complete destruction of the sample. Nevertheless, compared to unalloyed niobium, its oxidation rate was 4 times lower. The niobium 10 chromium 7 molybdenum 12 titanium 0.8 carbon alloy demonstrated significantly high oxidation resistance, forming a continuous oxide scale on the surface after oxidation with partial spallation of the scale. Unlike the niobium 7 molybdenum 1.5 zirconium 0.8 carbon alloy, which disintegrated after 3 hours, the niobium 10 chromium 7 molybdenum 12 titanium 0.8 carbon alloy samples retained the geometry. Compared to the niobium 7 molybdenum 1.5 zirconium 0.8 carbon alloy, which forms niobium 505 oxide scale, the high oxidation resistance of the niobium 10 chromium 7 molybdenum 12 titanium 0.8 carbon alloy explained by the formation of an oxide layer containing titanium niobium 207 and TO2 oxides in two modifications as butyl and anatase. Thank you for the attention.
Thank you very much. And I would like to ask if Sergei Schwab is here. Sergei Schwab.
Dear colleagues, good day to everyone. I'm instead of Sergei Schwab. Yes, some unpredictable circumstance couldn't maybe at the time. So our topic is third at the list. This one, yes. Thank you. I want to good day everyone. I present our research that is dedicated to experience of welding high manganese steels with high percent of aluminum and carbon. What is interesting, these kind of materials are relatively new and they are widely using in mechanical engineering. It's some kind of modern and very reliable material with even some perspectives for ballistic protection. It's unique. It has unique combination of strength, low density, toughness, and energy absorbing capacity. But it's a big problem to weld these kind of materials because they have complex microstructure, phase composition, and they are very sensitive to heat input during welding and heat treatment. So welding is the big problem for these materials. It's comparable maybe to cast iron, the welding of cast iron, so it seems to be almost unweldable. But we tried to see what would happen if we take this kind of steel in as cast state, and with described chemical composition you can see at the slide, and we took cheap wire with special commercial widely used wire of we call it SV08 G2S. It's with manganese and silicon, and try to weld this material in MAG welding method. As we can see, we obtained two welding zones in this welding volume, in the volume of seam, this part. If the heat effective zone what was obtained was about 5 millimeters, and the concentration of base metal in fusion zone not correct. The diffusion of alloying elements of base metal to seam metal was very predictable. This diffusion zone was about 2 millimeters, and what is interesting that the cracks were formed to the seam space, not to the base metal. And the diffusion of manganese was slightly lowering from the basic metal. The diffusion of aluminum was a little bit lower than the manganese, but we can see that it was relatively slight, and this is very good. So seam metal had low micro hardness because its chemical composition didn't change in the central volume, and then what is good that micro hardness was slowly rising to the overheating and normalization zone, and it's very noticeable that normalization zone has almost the same micro hardness and as the base metal, but overheating and fusion zone has lower micro hardness that is good from the point of toughness, but bad from the point that we could see earlier, the crack formation. So we need to work with chemical composition control, and another interesting part that recrystallization was very noticeable in heat effective zone. So our S-cast state was recrystallized during this welding process, and it recrystallized very noticeably. Now we had some more experiments, and they showed us that this welding wire we used is not the best way that could be chosen, and we took some another wire with high nickel content, and we didn't obtain cracks, and we didn't obtain such disadvantageable effects with chemical composition changes between seam and the base metal volumes. So it was our first step, and the investigations are in progress now. Thank you very much.
Thank you very much. And I would like to ask if Ludmila Nyrkova online. Are you online? Ludmila Nyrkova. Ludmila Nyrkova. And what about Marina Kobylinska? Marina Kobylinska. Marina Kobylinska, are you online? No? So I think it's all our agenda for today. And the first day of our symposium of metals and alloys is finished. Dear colleagues, dear auditory, and every participant who joined us, thank you very much for this great challenge, for this great day full of interesting reports, interesting discussion. And we are waiting for the next day, for the tomorrow. We will continue our discussion and we will wait for the new great reports. Thank you for everyone who join us, who follow us, who ask the question, and who make the great reports for today.
Thank you. See you tomorrow.
See you tomorrow.
Bye.
Bye.